chatter on the Clouder platform about difficulty connecting to Zoom rooms or something. I think some people are lost.
Oh dear. Yeah, my hope was this Clouder thing would make it sort of friendlier and easier, but it's not clear it's doing that.
No, it's it's got a bit of clunkiness to it, and it seems like a lot of people are a little confused about if these workshops are on Clouder or if they're on Zoom or how that works. So
yeah, I mean, Clouder actually doesn't have any of its own video streaming. It uses two different systems.
Yeah.
I think one's called Twilio or Tulio or something.
Ah, yeah, Twilio. Yeah, probably Twilio.
And that the sort of break rooms are Twilio, and that the speaking rooms are Zoom, which I'm sure adds complexity.
Yeah, in some cases you have information about getting to the Zoom, and in some cases you don't.
Yeah.
So that makes it.
And we are using two different Zoom rooms, so I'm not sure how that's going to work. I mean, I think the Splash Conference chair, or the workshop chair anyway, added links to, go to here's how you get into the Zoom room. But for ours, I hope he's going to change it after today's session, but maybe I'll remind him of that. There's a YouTube thing. I mean, I'm curious whether.
Yeah, that hasn't, I don't know if I'm muted or not. That hasn't gone live. It's waiting for streaming, so I don't know what's the deal with that. But it's been like
I show a little thing that says live in my screen share button, but I don't know if that means anything. Well, it's 10 a.m. I figure we give people a few minutes, and then I'll kick it off. Who knows how many people are?
Oh, we are streaming on YouTube now.
Oh, good. I show a little thing that says live.
Yeah.
With a small delay.
You better not be playing the video.
So we are all live
unmuted
now.
And watching the YouTube. That will really add some excitement. It looks like it's got a bit of a delay, or it sounds like it's got a bit of a delay.
Yes.
I told you, talking to the moon.
Yeah, that's the problem, because you don't know how many people are watching the YouTube streams.
That's true. It did say how many people were waiting, so it doesn't say anything about how many people are watching.
I didn't see anything. I didn't really look hard either, but so that doesn't say much.
So, hi, Miguel.
Hi, hello. Good afternoon.
Miguel, do you know Michael Clem?
Yes, we've met at Europe.
Oh, okay, right. Well, Miguel is going to handle the Q&A for your keynote. Michael, I'll introduce you, and then Miguel's going to take over. And hopefully people will find the chat, which is where the questions are supposed to be asked. And we've also lined up a few questions of our own, just in case the chat doesn't work.
I have to admit that I'm still a little bit, how to handle this Clouder plus 2 Zoom rooms, sort of, but it will work out well, I'm sure.
Okay. That's our optimist.
So I also got the chat window open in Zoom here, so
okay.
Let's see.
Great. Hello.
Hi, everybody. How are you doing?
Good. Hi, Sarah.
How are things going back there? How is the COVID situation being handled?
Oh, in the USA? It's the
Well,
same like
in
everywhere.
your state.
There's light at the end of the tunnel.
Yeah, really. I mean, you look at the numbers, and it's worse than it's ever been. I mean, in terms of infections, and even hospitalizations are beginning to match earlier peaks. So it's not good. Not good at all. Although it's nice to see those vaccines coming through, but that's still, 6 months away for most of us. So, okay, well, one more minute. I'll wait till 10:05, and then I will kick things off. I understand we're on YouTube as well. So hello out there in the YouTube land. We don't know how many of there are. We're hoping a few, but you can also, I think, join us on Zoom if you'd prefer. If you go to the program page or on the Splash HILT workshop web area, there's a program page. And it has links to the HILT Zoom room, the HILT YouTube room, and the HILT Clouder room, which I'll talk about in a minute. So I guess I'll get started here. Welcome to the HILT 2020 workshop. We've been having our workshops about every 2 years. This is the first one we've done totally in cyberspace. So I don't know if this will be our tradition going forward. My guess is will be kind of some mixture of cyberspace and real space in the future, because when the academic deans discovered how their budgets for travel suddenly didn't have to be very large, they're saying, wow, this is great, let's do this forever. We'll see whether the professors and their students complain that they're getting a little tired of sitting in their basement going to conferences. I hope you have maybe a better venue than that. My backdrop is artificial. I'm not actually there on beautiful Martha's Vineyard where that picture was taken. I'm actually in my older daughter's old bedroom. I think we all have our own little hideout spots. Each year we've had a slightly different theme. High integrity language technology is what HILT stands for. And this is a morphing of the annual or semi-annual SIG-ADA conference. I think the notion of having a conference just about a programming language is a little bit, dated, or it only lasts so long, because really people are more interested in domains of one sort or another than in languages, I would say. And often large systems are, mixtures of different languages and different technologies. And sometimes you don't even know where your program is running. It's out there in the cloud somewhere, and you're running on some virtual machine. And, so what's interesting is what you're trying to do, what you're trying to solve. And we've focused on places where the programming language or the language technology is a key part of your strategy to solve a high integrity problem. And this has been our sort of meta theme, if you will, for the last decade or so. We've had a number of conferences, and then we switched over to being just a workshop, because workshops are a whole lot simpler to administer, I have to say. And this one, we focused on the fact that, Moore's law of single processors getting faster kind of ended like 15 years ago, if you can believe it. And since then, we've been getting faster by having more brains on a single chip, and then by having more chips in a single, single place, or out in the cloud. And so, unfortunately, instead of just sitting around waiting for your program to get faster, you have to actually do something specific to make your program faster. Maybe rewrite it, heaven forbid, or at least do a lot of new pragmas and various things to try to make it take advantage of this modern hardware, which is both parallel and distributed and heterogeneous, and just a bit of a nightmare when it comes to trying to program this thing. My view is that we're sort of pushed back into machine level programming, where we're sending messages and we're worrying about data placement, all those things that we thought we didn't have to do anymore. That was the compiler's job. Now it's back to being our job. So we're trying to think, are there languages and technologies that will allow us to use all this exciting, crazy, modern hardware without having to be a complete specialist in the hardware. We want to stick with our interest in the domain and trying to solve the problem. So hopefully the programming languages and their technologies can help. So let's see if I can get this to actually, oops, there we go. Our overall program, the first day today is about parallel programming, a lot of it devoted to OpenMP, other parts devoted to Ada and the crossover between Ada and OpenMP. And then we also have a talk about the compiler intermediate representation. And I think that's going to be interesting because the panel is also sort of related to that, is can we bury some of the work deeper into the compiler and the infrastructure instead of having the programmers have to do it. And then tomorrow, it's sort of the distributed day, but it's really more the heterogeneous kind of higher level way of looking at the problem. And we've got an interesting keynote about ZeroMQ, which is a very nice, easy to use, relatively speaking, networking communication system based on sort of sockets, but simplified sockets. And then we've got various other ways in which people have tried to build distributed systems, both for Ada and for Java. And then we have a Python-based one. And then we're going to talk about Rust. And finally, our panel will be hitting sort of a general notion of how can languages help. Okay, so our goal is every talk we'll reserve at least 5 minutes for Q&A. There's a chat function, which you should be able to find at the bottom of your screen. You can click on chat. It should bring up another little window. And in that window, you can type your questions. And the session chair will be monitoring that. And when that question and answer time comes up, or if maybe the speakers break for a minute, any questions? Well, that'd be a time when the session chair would break in and read some of the questions.
Tug, I just want to interject also. The YouTube live stream has a chat window too, so we can monitor that.
Okay, that's going to make our job more interesting. But okay, session chair, now I'm going to split your brain into 3 places. Okay, we prefer you use the Zoom chat, but if you don't have access to the Zoom, then clearly your choice is the YouTube chat. And we're going to ask this.
We'll know you a little bit more. Clouder also has a chat.
Oh, great. Excellent. And we're going to ask the speakers to stay in the Zoom room afterwards, and there might be a chance for people to actually ask questions using their voice instead of the chat. We'll see if that works. I mean, a lot of this is, trial and error. And then there's also a break room in Clouder, which would be just if you want to go and talk with each other, schmooze, et cetera. Not everyone has access to that, but if you do, that would be an option. And we'll have 2 coffee breaks. It says get your own coffee, I'm afraid to say. Right after the keynote, and then about an hour later, we'll have a second coffee break. Okay, and let's see if I can, there we go. Oops, I skipped over. Today's keynote speaker, I'm very pleased to have Michael Clem, Dr. Michael Clem. He's CEO of the OpenMP ARB, which is the Architecture Review Boards. And as you can see, he has his PhD in computer science from Friedrich Alexander University Erlangen-Nuremberg, I think. And he was Intel until just recently. And he has been CEO of OpenMP ARB for a while, I'm not sure how long. But OpenMP is essentially a standards organization devoted to the OpenMP technology and trying to bring it forward. So without further ado, I'm going to stop my sharing and let Michael start up his.
Okay, unmute myself so I can talk to you, share my screen, and you should see my slides now. Is that accurate information on my side?
Looking good.
All right, cool. So hi, I'm Michael Clem. Thanks for the kind introduction. I'm actually CEO since 2016. So quite a while now, but I joined the ARB in 2009 as a technical contributor, and I keep continuing that role. Just for the sake of being of truth and transparency, and if my clicker would work, I can move to the next slide. A small disclaimer. So I'm an HPC person. My views might be skewed towards the HPC domain. I consider myself a dinosaur in that area because I'm doing HPC for oh my God, almost 15 to 20 years now. So that's quite a bit. My view is most certainly skewed towards the OpenMP API. That probably is part of my role. So I have to promote OpenMP in the community as the programming model of choice when you think about parallelism. And then for sure, this talk will be tainted with my own opinion. I will not hold back. And if you ask a question, you will deserve an honest answer. All right. So the OpenMP architecture review board, it has been mentioned before. Our mission is to develop OpenMP as an industry standard, as a quasi-standard. It is directive-based, multi-language, so C, C++, and Fortran. You'll see in a minute that we do high-level parallelism. So most of the task of optimizing and producing parallel code is actually moved into the compiler and into the runtime that supports the compiler. And our goals are to be productive, performant, and portable, right? So whatever you write in OpenMP should be portable across different vendors, both hardware and software. It not necessarily needs to be performance portable because that's a myth. But for a given architecture, you should be able to squeeze the last bit of performance out of it. And then the other key ingredient to OpenMP is that we're not a research project. While we have, as you see from the list of logos on the right-hand side of the screen, we do have a lot of research institutions on board, and we're tapping into research. But the main theme of us, of the ARB, is to standardize common approaches into an industry standard, right? We don't want to do bleeding edge research specifying a parallel feature in OpenMP that nobody ever has figured out how to actually implement it. We want to have, the common knowledge that is existing right now in the HPC industry or in the parallel computing industry, and we want to use that and standardize that as our OpenMP language. All right. So why do we want to do high-level parallel programming? Let me do something really simple. And as I said, I'm an HPC dinosaur, so I'm going to use Fortran. Okay. So here's a Fortran Hello World program that just prints Hello World on the screen, right? And we want to parallelize that. So here are the ingredients that we need. So if you want to do that in multi-threading, let's leave MPI aside for a second, okay? So if you want to do that multi-threaded, first of all, we need a different programming language. Fortran doesn't have any parallel mechanisms. By now they do concurrent. I have to admit that in co-arrays, but if you want to use a low-level machine interface like POSIX threads, you have to switch to something like C or C++ as a macro assembler to use that kind of library. All right, so then we need to outline the code that we want to execute. We have to have code to execute or create a bunch of threads, handing in that run function. And then, the red part is you have to somehow synchronize the threads so that the master can continue when the parallel work is done. Now, this might seem overly basic, and I admit that, right? But funnily enough, the C++ interfaces don't look much different. It's just that you have to have additional syntax to write the code that you outline in a lambda expression, so you don't have to really outline it. But the basic structure of the code remains the same, right? In a high-level language like OpenMP, that would look like this, right? Instead of figuring out how to do the gory details on this right-hand side and what basic low-level code you have to write to make things work, you can just write, okay, here's a block of stuff that I wanted to execute in parallel, and you're done, right? And for this simple example, it's probably oversimplified because the solution that I'm taking is actually very naive. But once you have alternating sequences of parallel and sequential code, it becomes really difficult to figure out how to actually send a thread to wait, right? So what should a thread be doing while it's waiting? And the deeper you dive into log algorithms, barrier algorithms, and all the low-level details, you will find that it's overly complicated to get this kind of low-level interface to perform efficiently, right? In OpenMP, we basically get that for free, or in most other high-level languages. Let's do something more useful. Okay, so here's a little bit of code, more HPC-ish. where we want to do an array sum, element-wise operation on two arrays, sum up each element of A and B and put it into C, right? So if we now take another high-level language, as they say, Circle, what you'll need is lots of boilerplate code around it. You will do explicit management of buffers, a lambda expression for the loop kernel, explicit synchronization via RAI, which is overly difficult because if you misplace a closing curly brace, you get an incorrect solution. And that's hard to find. I spent like in my life, like one day already trying to find these kind of things. So the code will look like this. Right? You don't have to really understand it. There's a little bit of buffer management going on to wrap the plain C or C++ pointers into a more enriched object that Circle can handle in terms of data transfers when it goes to GPU. Then you have to somehow describe the access mode, and then you have to iterate through using a special template that then accepts the lambda expression of your loop kernel. Okay, I actually initially planned to show you OpenCL code, but that font size would be too small because it's even more boilerplate code. So this is already quite good abstraction, but as you can see, it's still rather a lot of code that you have to write. In OpenMP, things would look like this, right? Just a pragma in front of your loop. You still have to deal with data management, right? But you just have to specify what you want to transfer, and everything else is handed over to the implementation to make it right. Okay, so what do we support in OpenMP? Everything here in green is supported by OpenMP. It basically starts up at the cluster level, so where we have multiple connected nodes between which you have a fabric like InfiniBand or Omnipath or Ethernet or whatever. OpenMP does not support that. Okay, this is MPI domain. This is Perl partition global address space kind of programming. We don't want to deal with that. We just are in the node. Okay, we can talk to coprocessors and accelerators like GPUs or TSPs, or if you will, FPGAs, if you have an implementation for that. And down the computer architecture in terms of nodes, packages, compute complexes, down to cores, hyperthreads, and vector pipelines where single instructions are processing multiple data elements. We support everything in OpenMP as a feature. Where you can, describe to the compiler what it should do with the code. Now, Tuck actually mentioned that in the introduction. At least I understood it that way. So there's a continuum of control. That's how I would like to call it. So on one end, the one extreme is a descriptive language where you express the what, like what is typically attributed to 4GL languages, so generations like SQL, or other high-level descriptive languages where you just describe, what kind of stuff you want, right? You completely typically ignore the implementation, so you're completely agnostic of how it's done. You just express what. But the thing is that you now have to rely on the quality of implementation, right? If you have a badly performing database underneath your SQL language, SQL language, then you get bad performance. If you have a high quality implementation, you get good performance. The other extreme, that's prescriptive. So this is where you express the how. That's like, assembly level or C level, where every machine detail is exposed to the programmer, and you really have to focus on the implementation of how you do things, right? And at the same time, you get the benefits that you can expose control over execution, right? And so OpenMP tries to address the whole spectrum to some extent. So let's say just pick an arbitrary work sharing construct that parallelizes loops. It's somewhere in the middle, right? You can either say just execute it on a bunch of threads. You can also say, hey, I want that specific schedule with that chunk size and that kind of aspect to the execution. There's OpenMP tasking. That's way more to the descriptive side, because basically what you say is, here's a bunch of code with its data that we can execute in parallel and go figure it out, right? Here's a task. Just do whatever you like with it. Execute it in place, defer it, whatever you want to do, it's fine, right? Pragma OpenMP loop, that's a loop construct that we introduced recently, well, 2 years ago in OpenMP 5. That's more descriptive, where you just say, hey, this is a parallel loop, go figure it out. And then there's this example that I already mentioned, a work sharing construct where you actually influence the schedule and the way the loop is mapped to the hardware and the caches of the system by specifically asking for a particular static schedule with a certain chunk size. Right? And so what we try to achieve in OpenMP is that we support a useful subset of this spectrum. Right? You don't want to be fully descriptive because then you probably lose too much of performance. At the same time, you don't want to do too prescriptive approaches because then your productivity is going to be limited, right? But the key thing is, regardless of where you start in this continuum, like if you want to start here, right? OpenMP should give you a path forward to the prescriptive world of things by giving you the right set of constructs to gradually move your code over from here to there. Right? So ultimately, you want to start on the left-hand side in the descriptive land, and you want to move to prescriptive expression of features wherever you feel a need because you actually need the performance in a certain part of the application. All right, regarding roadmap. So in 2018, we just released OpenMP 5. Now in November, this last week, actually on Friday the 13th. I hope that's not a bad sign for OpenMP 5.1. We released OpenMP 5.1. OpenMP 5.2, that's an intermediate release that we scheduled to do some rearrangements that we wanted to do in OpenMP and as part of the specification document. And then in about 3 years, in November 23, we will have OpenMP 6. So this gives about 3 years from today to influence the next version of the specification. In between, we're doing a whole bunch of what we call technical reports. These are essentially feature previews that we try to launch every year so that the community knows which direction the OpenMP ARB is moving OpenMP, and so that they can give us feedback. All right, the specification is now live. So if you browse to our website, you can have a look at that. If you are an old-fashioned guy like I am, who likes books and shelves, you can actually print the specification, or as kind of a service, we published all the OpenMP specifications, even the old one. The first one you can get as a book at Amazon. It's basically wholesale price, so they charge us for the printing costs. And we charge you for the printing costs, so we don't earn any money except for roundings between those two prices. So you can get it, you can put it in your shelf. It makes a nice bluish, greenish line of books in your shelf. It actually looks quite nice. All right, so what we did is OpenMP 5 introduced a whole lot of new features. That is probably the biggest release that we ever made in the history of OpenMP. There's a whole lot of stuff that we did, minor things or gradual things like improving the base language support to cover latest standards. We also introduced a way to talk about memory so that you can describe the traits of memory that you want from an allocation. We now support unified shared memory for GPUs. We can support collapsing of loops that are non-rectangular so that it can parallelize like triangular loops. We have new ways to express multi-level parallelism. We have parallel scans. We can do template metaprogramming. And I will have a couple of things in my presentation to show you what that means. Now, what OpenMP 5.1 does is it adds on top of those and improves the usability and the performance of those features. So we now have 20 support for C++. We have an error directive so that you can tell OpenMP to error out. We have an assume directive. I'll cover that in my presentation. We have loop transformation directives. That's more prescriptive stuff so that you can describe how to tile and distribute a loop more fine-grained in terms of the machine hierarchy versus the threading that you use in the back. All right. Let me quickly cover modern OpenMP programming. So OpenMP was founded in '97, and at that time you had, rather small scale shared memory machines. So this traditional work share approach would still work in the light of Amdahl's law. All right, so the way this would work is you got a loop down here that you consider parallel. You want to aggregate some result that is computed on a per thread level. So you could stick in an OpenMP pragma that describes parallelize that loop, do a reduction on the variable s, private as L, and schedule that whole loop with a chunk size of 4 statically on the machine. Right, and then what would happen is the master thread or the main thread would encounter that construct. It would fork a team of threads. However that's done, completely agnostic to the programmer. At the end, it would join all the threads like I was showing in my Hello World example, and then continue in the master thread. The work sharing construct would then allocate a bunch of private variables as temporaries for the per thread results, distribute the work of the loop iteration space, execute, do a barrier automatically, and reduce all the results. Right? Now, the problem with that is it really doesn't work. I mean, if you think about machines that we have today where we have like 128 cores, Amdahl's law is hitting you hard. Right? You cannot afford even having 1% of sequential fraction in your whole code if you want to achieve a considerable speed up on that kind of machine. So even the barrier down here is going to literally kill your performance. Right? So there must be something else. And the way I think about OpenMP programming, and most certainly other people, probably Sarah as well, let's see if she agrees with me. So the modern way to program OpenMP is task-based, right? We support work sharing for the legacy, right? And we will carry forward improving those features so that people who really rely on these kind of features can see improvements over time. But ultimately, we are kind of promoting to restructure the code into a task-based execution model where you can execute in parallel on unbounded loops like while loops, where you can parallelize easily recursive functions, where you can have either a single creator, multiple creator scenario. You can nest tasks, and you can nest tasks with work sharing. There's a couple of indirections how you can make OpenMP way more composable in a large application when you think about tasking. And the other people on this call, they know that I was advocating that anytime I was speaking to them. So here's an example. Here we're running through a while loop, iterating over each element, and for each element we spawn a compute task. And what happens at runtime is that conceptually these tasks are then moved into a task pool, and idle worker threads will grab a chunk of work, a task with its data, execute it. And as long as you create a task, you got parallelism. And when you're no longer creating tasks, like when the while loop ends, your code also ends, and you're back to sequential. Right? And the way this then would work is that you start parallelizing at the very top of your application and not at the lowest levels of your loops or your kernels, but rather you start at the very top, so that you get as many parallel tasks out of this application as possible. Here's an example. So here what we do is, this is Cholesky factorization to decompose a matrix in a certain way. There's a couple of math functions that we have to invoke. Each of them can be a task. And now the thing is, between the purple task and the blue task, there's data dependency, because this guy up here is going to prepare data that this guy down here is going to need. So we have to put in some synchronization. And what this means is that you get this lockstep work share kind of behavior where you have a bit of parallelism, then you synchronize everybody, you have another subset of parallelism, you synchronize everybody, and so forth. With OpenMP 4 and carrying forward with OpenMP 5, 5 and 5.1, we considerably extended the way tasking works. So now you can still use tasks, but now you have a way to describe dependencies between those tasks so that the implementation can figure out a natural schedule, how to schedule those tasks that you create throughout your code in a way that they don't break those data dependencies, and at the same time to achieve as much parallelism as possible, right? And so when execution units are taken, as you can see up here, you got a much bigger amount of parallelism going on than on the left-hand side of the screen. And here you got maybe you got free compute units that you can use for other threads and other tasks to execute. All right. one of the things that we also did is kind of to enforce this vision of OpenMP tasking being the parallel model of choice for OpenMP programmers is I already kind of sketched how to do GPU offloading. And the way this initially worked is that it's completely bulk synchronous. So that means while you're on the GPU or on your accelerator, the host would actually stop executing, at least that host thread. You can now add the no wait clause to it. So that turns this accelerator usage into an asynchronous one so that the host thread can still continue executing. And in OpenMP speak, that no wait here turns that whole offload region where we use the GPU or the TSP or whatever, they now become an OpenMP task. And with that slight change of the OpenMP specification that we made, you get now the whole support of tasking on top of GPU offloading. So what you can now do is you can have a host task like this purple one that initializes some data in array A, and you can have a target task that is asynchronous. This guy up here is also asynchronous. And you can describe the dependency of the offload task that is running on the GPU towards the host execution, right? So you can introduce this dependency between the purple node in the task graph and the blue one down here, right? And you can do that for all your offload regions, including the ones that you have coming from OpenMP regular tasks, right? Like in the Cholesky factorization, right? And when you execute that, you can get synchronization between the offload regions, but also with the corresponding host execution that prepares the data for the GPU or your accelerator, TSP, FPGA, and whatnot, right? So that's a way how you can really marry this heterogeneous approach where you do TSP usage, GPU usage with the usage of parallelism and concurrency on your host, so that ultimately both worlds become like a tightly integrated solution for the application programmer. All right, I already mentioned OpenMP metaprogramming. It's not as expressive as probably C++ template programming, but it allows you to use directives to construct other OpenMP directives depending on the OpenMP context that you're in. A way to specialize code for different execution contexts, and to inject special implementations for algorithms. Okay, let me give you an example. So here what we want to do is, here's a target construct. So you want to do something like a GPU offload, right? For that loop down here, right? And then when you figure out that this thing, that whole region of code is compiled for an NVIDIA GPU, right? Then you would like to substitute that construct. So it should then read pragma OpenMP target teams loop, right? Whereas in the other case where it's not a GPU or you're running on the host, then it should just be parallel loop, right? So you don't bother with creating a bunch of additional execution teams for a really wide parallel device like a GPU, right? The other way how you can think about this is, you could say if this is a function that is specializing a BLAS call, or that's a BLAS implementation that you did, and you figure out that you're compiling with the Intel compiler and then MKL is available, you could substitute a function call doing this with a call to MKL if that's available to get more performance out of it. Even without rewriting your full code, you just declare your function in a way that it's compatible with MKL, and then you can inject a different version depending on the compilation context that MKL is available. Or you could go as far as, even supplying a CUDA written kernel function that you compile with the NVIDIA CUDA compiler, and then you can say, well, if you figure out that you're compiling for an NVIDIA GPU, don't use my code, but use that other GPU code that I wrote in CUDA, right? All right. Let me give you some 5.1 news. I cannot cover each and every aspect of OpenMP 5.1 because that would be too much. I just picked a couple of things that I quite like in terms of what we did and how to improve OpenMP 5.0 features. So the first one is in OpenMP 5.0, we already started to get closer to the low-level interfaces. So, you know, even though OpenMP has kind of a closed world assumption, the reality is that in a big, at least HPC applications, likely other applications as well, there's always kind of a low-level interface that you probably want to use to do something. Like, for instance, if you do OpenMP on the host, there's likely P threads underneath implementing the OpenMP functionality on your parallel system. If you think about an Intel GPU that is coming up, and you know Intel's one API beta is just running right now, you will have OpenMP running on top what they call level 0. Okay. If you compile OpenMP for an NVIDIA device, then CUDA will somehow sit underneath the OpenMP implementation. And so the question always was, how can those two worlds interact? I mean, even though I said on my continuum slide that OpenMP strives to address the full continuum, or at least a useful subset of it, there are programmers who are desperate enough for performance so that they would use something like CUDA or level 0 to program directly against the available hardware, right? And so how do those two worlds interact? And with OpenMP 5.0, what we did is you could actually ask for the data buffers, right? So there was a way to say, OpenMP, give me the underlying OpenCL level 0, whatever buffer object that you are using to store my data on the GPU. And so you could take that object and stick it into the CUDA interface, if it's a CUDA buffer, or into the OpenCL interface to get that data into the OpenCL or CUDA world, right? There was also a way how you could convert the OpenCL buffer or the CUDA buffer into something that OpenMP would understand, right? So that you can allocate data in CUDA and use it from OpenMP. Now, what we did with OpenMP 5.1 is that we introduced the interrupt construct that's shown on that slide here. And the basic idea is that you can now query the underlying implementation for implementation specific details. Like, for instance, in this example, what I'm trying to do is I'm getting out the CUDA stream, right, that OpenMP uses to send work and data to a GPU. So I can now get that CUDA stream object out of the low-level implementation and then call cuBLAS, so NVIDIA's implementation of math functions, on top of that stream so that it automatically synchronizes with the OpenMP offloads that I'm doing from elsewhere. Right? It looks very convoluted, to be honest. I fully buy that, but we are now in the turf of being very, very implementation specific, right? So this is also not really portable, right? You can still ask, get me the interrupt property for, the internal thingy that you're using, and then you can ask, okay, is this thing that I'm talking to, is that a CUDA device? And if yes, do this, and if not, do something else, right? So there's a bit of code that you have to write, but you don't have to fully leave OpenMP land to now use something like low-level CUDA stream interfaces. The other thing that we did, that may seem like a weird change. So, and some of the reviewers for my keynote actually asked the question about, hey, what's your backward compatibility? And, the story typically goes, we're not breaking backwards compatibility, at least if we don't think it's useful. And I have like 3 instances in like 23 years now where we are about or actually broke backwards compatibility. And this is one of them. The other 2 are, we deprecated a stupid feature that they put in from the day one. It's called nested. The way how you deal with nested parallelism was always like stupid. So we deprecated that one. It's going to be going out of OpenMP in 6. It's deprecated now. The other thing that we did is we are now more specific about how loop scheduling works. And if you are really crazy and you test it for monotonic and non-monotonic behavior in loops, like the way OpenMP hands out the schedule to the threads, you may lose backwards compatibility. And that one is the third one where we are breaking backwards compatibility by deprecating the master construct. And we're replacing it with this construct called masked. So it's not much more to type for you. So if you compare master and mask, it's just 2, the Hammond distance is like 2. But the way this works is the master construct would only execute on the main thread of your code. It was very specific that it's always the thread that has ID 0. And now with the mask construct, you can add a filter clause to ask for a specific thread ID. So now you can say, well, I don't want to execute that on thread 0, but rather thread 14, because it just makes sense for you to do this, right? So master and masked are the same. If you add the filter clause, you actually change the default thread 0 behavior to be something else. And in future, likely in OpenMP 6, we're going to extend that so that the filter clause can be a Boolean. So you can evaluate an arbitrary expression. And if that mask or that filter clause evaluates to true for that specific thread, it's going to execute the masked code. If it is 0 or false, then it won't execute it. The other thing that we plan to do is to have subsets so that you can describe, every odd thread or every even thread or every thread that has a prime number as its thread ID, whatever interesting reasons you come up with to have these kind of conditions, you can then use. The scope construct is another one that we added. It basically is a directive to execute a structure block by all threads. Doesn't sound useful at first, but the expressiveness comes in when you think about the clauses that you can add to it. So until now, OpenMP only had very specific work sharing constructs that would use all the threads, like parallel for loops, or it would have like the single construct where an arbitrary thread is picked for execution. And why this is useful is there was no way to have a reduction or any other global operations going inside a parallel region. The only way how you could achieve this is this pragmatic pattern by having like a dummy for loop that iterates across all your threads, increment 1, so that every thread would get 1 iteration of that loop so that you can use the reduction clause on the work sharing construct. And so this is now a much better, much cleaner way and much more syntactic way and semantically well-defined way of dealing with that kind of situation. And in the future, we also plan to extend that scope construct to cover more use cases on top of this simple use case that I'm showing on this slide right now. All right, the assumes directive is something where you as a programmer can provide to the implementation additional invariants or context information so that you can exploit it for optimization. So the way you can work with this is, so you can say, well, the following constructs are absent from this kind of code region so that the compiler doesn't have to take them into consideration when optimizing code. Or you can specifically say, well, this code and the call tree contains the following listed constructs, right? So that the compiler is simply aware of what's coming if it doesn't know all the code locations that you're talking about. You can give a like an assertion for a condition. You can say, well, this pointer is always aligned to like 64-byte boundaries so that the compiler can include that into the optimization pass. Or you can say, well, there's no more OpenMP coming. This is just plain sequential code, so don't bother with thinking about that it's going to be running parallel. You can say, well, there's not going to be any call to an OpenMP API routine. Or you can say, well, this is purely sequential code. We are not going to do any OpenMP tasking, implicit or explicit, no SIMD execution, no nothing, purely sequential scalar code, right? Here's an example. So what we can do here is, if we have a function that has a parallel region inside of it, where we know as the programmer that we are not doing any OpenMP tasking, we can say, well, pragma assumes absent task and task wait. So we're not using OpenMP task features. Then we launch the parallel region, and then we call, functions, and we have a barrier in here. Now, if the compiler doesn't know that there are no tasking and no tasks going on, then this barrier has to be a special barrier that is capable of executing tasks so that no task is still alive coming from that function when the barrier is left for the second code region down here. If the compiler knows that there are no tasks, it can use a different barrier implementation that is like twice as fast as the task-enabled barrier, right? So this is an optimization that a compiler typically cannot figure out if there's a call stack, but now we have a mechanism so that the programmers can supply that additional context information to the OpenMP compiler. And then C++ attribute syntax, that is something that we came up with. When you read through the C++ 11 promotional paper, I would call it, that introduced the idea of OpenMP, of attributes in C++, they actually used OpenMP as an example. So we're really proud of that. And so we thought we returned that favor to the community by adhering to their idea and telling them, okay, now it's here. So now you can get rid of this, to be honest with you, awkward looking pragma syntax in C++, and you can use something that looks more C++y and that actually supports C++ template programming. So these things down here, they are now true C++ features, and they can use templates to do this. And let me just show you the community reaction that we got for that single feature, which kind of makes me proud. So here it is. This guy was really cracking up on us doing that. He writes, oh my God, instead of pragma, C++ attribute syntax can be used to specify OpenMP directive, which simplifies their integration with templates. He was really happy about it. Must be a C++ programmer, I suspect. All right, now, since we're at HILT, just a couple of slides about functional safety in real time. I guess you want to hear about that. So here's my HPC tainted summary. Better not. The reason for this, and Sarah actually quoted that on LinkedIn this morning to promote the panel. So here, an implementation of the OpenMP API is compliant if and only if it compiles and executes all other conforming programs. It doesn't say anything about the incorrect programs, right? So basically, an OpenMP implementation that is compliant to what we require as the ARB is compliant if it completely screws up the execution of an incorrect program, right? So we don't have any mechanism to detect failure or incorrect execution. We're not supposed to have it, and most implementations actually make use of that fact. And I'm happy to debate that, whether it's good or bad in the panel. For sure, these semantics are geared towards maximum execution speed, right? We can save a whole lot of checks at runtime if it just can do anything, including collapsing all of the universe in the big crunch, right? We don't have to be specific about resilience or safety, okay? And this is a matter of where OpenMP is coming from, right? In HPC, it's simply annoying if your simulation crashes, but it usually does no harm, right? You lost a couple of compute hours, whatever. You submit, you fix the bug, you change the number of nodes or whatever, the number of threads, you run it again. If it goes through, fine. Except for burning some CO2, you didn't do anything bad to the planet, right?
Michael,
So
just three more minutes.
okay, I'm almost done. All right, so here's an example why this is going to be relevant for the discussion, right? If you put in something like the number of threads should be -42, actually the programmer cannot be quite sure what happens, right? The OpenMP implementation may have a sensible default for that. It may terminate the program. It may do anything, right? If you launch a parallel region in that context, how many threads do you actually have here, right? It may be 1, it may be 42, it may be 100. You simply don't know. Even if you used a sensible number like 16 up here, you cannot be sure that you actually get 16 threads down here, right? We had to address this to some extent with the cancel directive, right? But that's more a hammer that makes the problem look like a nail rather than a solution, right? So what we would require is a full error model so that it can actually catch these kind of mishaps, right? And reason about what happened and basically either correct the error or at least somehow handle that error in a cleaner way than, you know, unspecified behavior because you got a non-conforming program. All right, how does the future look like? So we will have more support for descriptive specification and prescriptive control. We will certainly improve the features that we have. So one of the things that we try to address is in memory is to have support for non-volatile traits, to improve memory affinity and to better reason about complex memory hierarchies. We're talking about having 3 agent threads. This is an idea that you can borrow from TBB or other parallel programming models, where when you start your program, you just have your workers available and you can just start executing. Whereas in OpenMP, you first have to create a parallel region. There's a proposal for event-driven parallelism that we have on the table. Not sure if you're going to get that in. We will certainly complete support for new normative references. So C++ 23 comes to mind, or Fortran 2018, or whatever is coming. 22, I think, is the next step. And then, you know, this is looking at Sarah and Eduardo. Support for safety critical and real-time systems. This is something where we have kind of a study group, but the study group needs to be a little more active. We have seen a couple of presentations about this topic, but we really need to see more and tangible proposals how we can subset and slice and dice OpenMP so that it actually works better. All right, so summary. 5.0 and 5.1 were a major leap forward for the OpenMP programming world. That's probably the biggest release series ever in the history of OpenMP. The 5.1 release actually went way bigger than we initially anticipated. It is now a modern directive-based programming model. So multi-level is supported from, you know, heterogeneous systems with GPUs down to regular multi-level threading to SIMD. We have good coverage of all what is kind of state of the art. It is actually a powerful language. I was only scratching the surface like maybe 5%. And the idea here really is that you have high-level access to parallelism and a path forward to highly efficient programming should you need that control without leaving the OpenMP model altogether. And then if you want to engage with us, we have a series of conferences. OpenMPCon unfortunately was canceled this year because of the situation that everybody is suffering from right now. Then there is IWAM, the International Workshop on OpenMP. So we're welcoming user interaction, networking, scientific papers, progress reports, questions, failed applications of OpenMP, and these are really a great way to engage with our community and the ARB members. And then there's the OpenMP users group if you're from the UK, soon to be non-Europe, but anyways, this is kind of a European-centric conference. Basically the European version of OpenMPCon. And if you're more interested in HPC, and if you're not, you can still come, supercomputing and the additional supercomputing in Europe. And if you want to know more, check out our website, openmp.org. It contains all sorts of information, including the full specs as PDF, HTML, and all the links, recordings, tutorials, whatnot. That's it. I'll be quiet now, except for answering questions. Thanks for listening.
Okay. Tucker, you'll be leaving to another room, right? I'm just asking. So I think I'm handling the Q&A for this keynote. So Michael, thank you very much for the talk. Unfortunately for me, the last part was short for the safety and real time. So I hope we have plenty of time to discuss that. But since there is a panel later on the topic, I will leave most of that to the panel. I think there'll be a very, very interesting discussion later. So
I'm going to refer you back to my disclaimer that I'm an HPC person.
As a real-time and embedded guy, I accept the disclaimer, but obviously I have also my own. But I will try not to go into that direction, because since there is a panel, I think that there will be a very nice discussion later on that topic. So I think that can be there. In meanwhile, during your talk, there were a few questions that were being placed in the chat. Okay. So I was double checking, and there is none in YouTube or Clouder. So the questions are only in Zoom chat. I don't know if you have access. You can read the questions there.
I got it open. So the first one is, if you are using OpenMP task-based features, why would you ever mention a thread ID? The simplistic answer is you shouldn't. But we still have this two worlds, right? We have the multi-threading world where threads are exposed by their ID and by their identity and behavior, versus the task world where you actually don't care about those kind of specific implementation details. And since OpenMP supports both, you can still ask for a thread ID, right? Even though you should not. In most cases where you're asking for a thread ID, it's either supposed to be for debugging so that you know where you're executing, or what you shouldn't be doing anymore is to do your own data decomposition scheme. Like, if I'm thread 7 out of 16, this is the chunk of work that I'm getting. That's kind of discouraged, but you can't prohibit it. And so, we have to deal with that situation, and it has all sorts of weird corner cases in the specification because that is still possible. All right. Richard asks, what happens if the programmer gives incorrect assumptions? Well, as usual, you got a non-conforming program. So, if you say this code doesn't use OpenMP tasking, then you got an incorrect code, it's non-conforming, and then OpenMP can either do something useful for you, like pretty much ignore the OpenMP task construct that it still encounters, or it can completely blow up your code, fail at arbitrary places in your code, whatever. It's just unconforming, and that means the behavior of the code is completely unspecified. Okay, has OpenMP effectively replaced OpenACC? What about CUDA and OpenCL? All right, so OpenMP is a superset of OpenACC. There are still programmers on this planet who like OpenACC better, and that's their choice. I mean, this is another industry standard for directive-based offload programming, specifically targeting GPUs. OpenMP is more flexible in that you can use any accelerator. So you could program an FPGA using OpenMP. You can decide whether you will want bulk parallel, data parallel loops, like in a GPU case, or if you have an accelerator like rest in peace, Intel Xeon 5 coprocessors, where you could use regular OpenMP tasking. You have pretty much the choice what is the best parallelization model for OpenMP on that device. Whereas in OpenACC, you got your parallel loop construct, you got your parallel kernels, and that's about it, right? There's probably one or two features where we violate the superset feature or syntax and semantics of OpenMP versus OpenACC, but for what matters, it's basically the same. It's a superset. And then what about CUDA and OpenCL? Well, we do acknowledge that these languages exist, also HIP from AMD, if you will. The thing is, there are good reasons for those languages to exist. And if it's just performance, right? My vision is that everybody should be using OpenMP. And unless they have a very specific performance problem that they can't solve with OpenMP directives, they need the mechanisms so that they can smoothly transition from OpenMP land to CUDA land or OpenCL land. And we tried to improve that situation in OpenMP 5 and 5.1, as I was showing, where, you know, in 5 we could at least have data access going back and forth between CUDA, OpenCL, and OpenMP. And now with OpenMP 5.1, we can even have stream access so that we can also access the underlying execution mechanisms. All right, and then Sarah was asking, are prescriptive and tasking incompatible? Because we actually need that. Well, tasking is unfortunately, a more descriptive feature, right? Because all you do is you mark your piece of code, you call it an OpenMP task, and you basically hand it over to the OpenMP implementation through the syntax and the semantics of OpenMP, and OpenMP will somehow figure out what to do with that task, right? So it's completely free to execute it in place where it's at right now. It may defer it. It may do whatever it likes, pretty much. There are some features where we try to restrict the flexibility of OpenMP, like by calling it mergeable and final tasks and all these kind of additional tasking features that we put in. We also restrict the freedom of execution where, you know, through dependencies and synchronization constructs, you can restrict the behavior of OpenMP, but ultimately tasking is going to be one of those features where probably they're more in the descriptive world than they're going to be in the prescriptive world. Okay, and then there's another question. Could the device model be the basis for more general distributed computing support? Yes, so Intel, when they still had the Xeon Phi processor, they had a feature in their OpenMP implementation called offload over fabric. So when you wrote an OpenMP target construct, it would actually send a message over the fabric of the cluster to a remote Xeon Phi node and use that as an accelerator. I have seen a research paper published at IWAMP 2, 3, maybe 4 years ago, where they actually used OpenMP target construct to send compute to, I believe it was the Amazon cloud. Right? I mean, the latencies are kind of critical, right? Because you have to pay the price for the data transfer over the internet to the Amazon cloud, pay the price for the transfer back and invocation cost and everything. But technically, it does work. The only thing that we don't really support right now is a bulk synchronous launch, right? So what that means is where in MPI or in any other distributed computing model, you can say launch like 1,000 ranks or 1,000 processes somewhere on the system, right? And it does that in an efficient way. In OpenMP right now, you have to enumerate the individual target constructs one after each other, right? So that kind of limits the scalability of how you can launch a whole bulk of offload regions on different nodes. That kind of is a natural boundary. But technically, when we solve that problem as part of the syntax, then I don't see any reason why you couldn't offload to, over the fabric, Amazon Cloud, Google Cloud, send the message around the moon and make it come back. The device model is capable enough that even like once I gave a tutorial where we actually played offload device with the audience. So my co-presenter and I were going to each and every one. We gave them a little task by handing them like a yellow sticky paper with a compute task on it. And then we collected all of them after they did it. And that was as part of the OpenMP specification. That would have been a valid offload device.
Okay, thank you, Michael.
You're welcome.
That was great.
Thanks for having me.
anyone who has any other questions for Michael, you've got a few more minutes to just unmute and ask them. But we will start up again in 7 minutes. And I think I know who the speaker is going to be.
So I have one question also, which is, so when I learned OpenMP a few years ago, so it was still thread-based, homogeneous. So, and lately OpenMP has been growing a lot, and now integrating a lot of different models. Okay, so well, we were just talking about general distributed computing, so maybe that's next. At the same time, you are integrating in the specification. So the specification is getting very big. It's abstracting so that you can go everywhere, but at the same time, you are putting ways that people can hook into the lower layers, into adding different non-OpenMP depending on the particular architecture or platform that they're using. Wouldn't that be risky that OpenMP starts slowly not to be portable? That people tend to use a lot of the low level, the non-OpenMP features and make it non-portable in the future?
Yes. Let me answer the question coming from the perspective of a GPU programmer, right? Like 10 years ago, when OpenMP didn't have offload constructs, and OpenACC was not existing, by the way, either, the only way how you could make usage of an GPU was by going to NVIDIA CUDA and rewriting, a good share of your application in that language. Right? So that is the definition, the core definition of being non-portable. With OpenMP and OpenACC, by the way, same answer essentially. The hope is that for those cases, or for most of your cases in your application, that you get whatever good enough performance, right? So that you don't have to go to CUDA to actually use that device. You can use OpenMP and it gives you enough of performance so that you as a programmer, or if you're a software vendor, your end users are happy with the performance that you're getting. And then hopefully the subset of code in your application that actually needs that kind of level of control is so small that the task of moving it over to CUDA and interacting with a low-level interface, yes, it does make the code non-portable in that regard, but it should be so small that it's easier, not easy, but easier for you to adapt that piece of code to a different architecture, because it's just a very tiny subset of all the code that you're writing. So that is the vision, right? And we are right now working towards proving that this goal can actually work.
Okay, so thank you very much. I don't know if there are other questions going on.
I haven't seen anything in YouTube or Clouder.
No, I don't think so.
Thank you again, Michael. And
you're welcome.
You'll be back for our panel, I hope, and maybe you can stay for some of the talks as well.
Yes, I will just quickly step out for a quick coffee, and then I'll come back for your presentation.
Okay, great.
Yeah.
All right.
So we'll be going again in 3 minutes.
Okay, is it in the same room, Tucker?
Same room, conceptually anyway. You don't have to be in the same room, but
Okay, couple of minutes then.
Okay, so it's 11:15. I guess we're ready to go.
Give people another minute,
Right.
maybe.
Yeah, okay.
Richard, do you see the full screen with nothing hidden?
I mean, I see the window you've got there. Not the full presentation screen, but it's in a browser full screen.
Okay. I think that's all that it's possible to do with
Yeah,
with the Google slideshow.
should be fine. Okay, so for those in the Ada community, I don't think Tucker needs much of an introduction for everyone else. So also of course, the co-chair for this workshop. So Tucker led the development of the Ada 95 standard, which also happened to be the first object-oriented language to be standardized ever, and continues to play a leading role in the development of Ada, including the upcoming Ada 22X standard. Tucker graduated from Harvard summa cum laude in chemistry before joining the Harvard Radcliffe Student Computing Center as a systems programmer, and then went on to join Intermetrics in 1980 as chief scientist. And Intermetrics was one of the original 3 companies to submit a proposal for the original DoD initiative that eventually became the Ada language. And although Intermetrics' proposal was not the winning proposal, they remained heavily involved in the Ada effort with Tuck's leadership, and delivered one of the first Ada compilers, actually. As mentioned, Tucker led the Ada 95 development effort during this time as well. And then he went on to found SoftCheck in 2002 before joining Ada Core 9 years later. And Tucker is now currently the Vice President, Director of Language Research and Model-Based Toolset Product Architect at Ada Core. And today we'll be talking about a layered approach to mapping AdaMP, a layered mapping of Ada to OpenMP.
Okay, thank you, Richard.
A little stutter even.
So I think it would be interesting, I think it will be interesting to take what Michael has just told us about OpenMP and think about how it could be mapped to a programming language where safety and security are actually very, very important. As Michael was saying, the OpenMP philosophy is, here's a very sharp tool, and you can do whatever you want with it. And if you happen to do the wrong thing, that's not our problem, it's yours. So I would say it's somewhat in the C programming language theory where, here's some sharp tools, we'll get out of your way and let you do what you need to do. Ada's got a somewhat different philosophy, and it's interesting to try to combine the two, hopefully get the best of both worlds, not the worst of both worlds. So I'll talk about how we've decided or plan to integrate OpenMP with Ada. And first I'm gonna talk a little bit about where Ada 202X is going. It should be coming out in the next year. So X is hopefully gonna be a 1 or a 2. Anyway, so come on, here we go. So a quick outline, introduction to Ada 22X, and then how OpenMP we're proposing to fit that into the picture. So what were the overall goals of Ada 22X? Well, parallel programming was actually one of the key goals of Ada 22X. We started talking about it in Ada 2012, which is when the prior version of Ada came out, and didn't really stop talking about it, and we're still talking about it. It's become surprisingly controversial, and I don't want to go into all of the politics, but we're still somewhat debating with various vendors about whether they want to step up or they want to be, the last one or the first one out of the block with lightweight parallelism. To me, it was a slam dunk, but for other people, it seems like, well, our customers aren't asking for it. Well, I think most programmers don't sit around thinking about, I wish their language had some other features, because they have to live with what they've got. But in any case, from a standards point of view, it will definitely have parallel programming. And from an implementation point of view, it may be a couple of years before it's sort of full industrial strength, if you will. Ada is always focused on safety and security. And in 2012, the Ada version adopted so-called contract-based programming with preconditions and postconditions and type invariants and so on. So there's a certain notion that you establish a contract when you're defining a piece of your program, and then the compiler or the runtime or both will try to verify those contracts are correct. And that feeds into parallelism as well. And then expressivity, which is one of those things that, it's sort of an open-ended list of good ideas that maybe are worth adding. I mean, that's always a debate. Are you making it easier for people to use the programming language or harder by adding some new feature? So one thing that in the early days of this discussion, there was a lot of debate about what does it mean about concurrent programming versus parallel programming. Ada has had concurrent programming really since the beginning, but they're sort of heavyweight threads. They call them tasks just to make things very confusing. I'll try to say Ada task when I mean an Ada heavyweight thread. And they correspond to when you've got multiple things to do, or there are multiple threads in the environment that you're dealing with. Maybe they're hardware devices and you've got a controller for each device, or you've got connections to other systems outside. And so you create a separate Ada task for each of those separate things you want to do. And then you do that even if you only have one physical processor. It's still valuable to structure your program as a set of Ada tasks if it's doing multiple things. And then there's a whole business of scheduling. And if you haven't got as many processors as tasks, well, then there's the priority-based scheduling, and there's earliest deadline first scheduling, and so on. A whole lot of interesting problems with scheduling. So what's parallel programming as opposed to that? I would claim parallel programming is when you really fundamentally have a small number of big problems to solve, and you need to apply multiple physical processors to solve a single problem. And so it's sort of the flip side in some sense. With concurrent program, you have multiple things to solve, and you might only have one processor. And with parallel programming, you have one big thing to do, and you might have many processors. The other point about parallel programming is there's no point in doing it unless you make the program faster. Whereas concurrent programming, you're structuring your program in a way that makes it easier to understand and maintain. Parallel programming, you got a perfectly decent looking sequential program, and now you're mucking it up by trying to make it use multiple processors. So it's in some sense, it's a very different problem. Concurrent programming, I would claim Ada has had great building blocks from very early on. Tasking and rendezvous, and in Ada 95, we added protected objects for sort of data-oriented synchronization and so on. Parallel programming, really nothing there. If you try to use Ada tasks for parallel programming, it's very heavyweight, not only in terms of the syntax, but also in terms of the semantics, because Ada tasks typically map one-to-one to kernel threads. And as was mentioned in Michael's talk, if you're creating and getting rid of kernel level threads on a regular basis, that's very expensive. You don't want to be talking to the operating system that many times. So
Tucker, sorry to interrupt. I'm just making sure, is your presentation slides, are they supposed to move on from the first slide right now? Because right now we only see the first slide, and I just had a comment about that.
Oh dear, that's not good. Well, let me stop and start again, see if I can figure out what's going on.
Sorry, I didn't pick that up earlier. There we go. I think we're looking at the
wow.
screen.
Sorry about that. Well,
Now
I'll show you a couple earlier slides.
Oh my gosh.
Do you see that earlier slide?
Yes. Yes,
okay.
Looking good.
Okay. Anyway, so you missed my big graphic here. So as far as parallel programming, we really want to make it easy and safe to write parallel algorithms. We want to hide as much housekeeping as we can, have the compiler detect safety issues, data races, and so on. And the thing that I'm going to talk about today is we want to enable the use of multiple lightweight threading systems. OpenMP is sort of the obvious one, the big gorilla out there, and we just heard an hour description of how amazingly cool it is and how effective it is. But given that we're talking about safety critical systems, we're talking about embedded systems, we're talking about real-time systems, it may be that OpenMP is not necessarily the right answer for all of those environments. And so one of our goals was to allow you to plug in a different lightweight thread scheduler, or none at all for that matter. If you want to just say, well, I'm going to write this thing as though I have multiple threads, but in fact, I want you to just fall back to a sequential implementation. And so that's sort of a goal that we believe is pretty important in the context of a safety critical embedded system real-time language. So anyway, just a reminder why this is important. It's been 15 years since the good old doubling every 2 year and speed thing ended. 2005 was when we hit pretty much 3 gigahertz, and we're still pretty much at 3 gigahertz. Maybe it's gone down sometimes in some of these new processors, because when they go multi-core, they sometimes also reduce the rate. So we have to solve the speed problem, not by just sitting around hoping for a faster single processor. We've got to take advantage of multiple processors. So for Ada22X, our goal was to not perturb the syntax of the language in a great fashion. And we sort of knew we wanted to fit the word parallel in there somewhere. And we played around with exactly where it would say parallel, but ultimately we settled on having it right at the beginning. And also over time, we felt, well, we want to have some control over the level of parallelism you're introducing with the parallel construct. And so we allow you to optionally specify the maximum level of parallelism to be introduced for this construct. So by saying 2 times num CPUs, what that's saying is that I don't want you to use more than, if I've got 4 CPUs, I want more than 8 threads, if you will, to execute this, or 8 lightweight threads to execute this loop. And the reason I have more than the number of CPUs is that way some of them may be bigger than others in terms of how much work they have to do. And this one doesn't look like it, but you can imagine cases where you don't actually know. You create a bunch of lightweight threads. Some will end up needing more servicing and others maybe not. So anyway, so this is the basic structure. You add the word parallel in front of a loop, and there are a growing number of kinds of iterators in Ada, and we pretty systematically have said you can put parallel in front of any of them. Some of them are building up a data structure, others are looping over a data structure, others are just looping over a set of values, and so on. So that's the first one. The other one is sort of a divide and conquer kind of thing, where you can have a parallel do, and you might have recursive calls inside the various arms of this parallel do. And in fact, the simplest representation of this is actually a parallel loop, where you go from 1 to n, where n is the number of alternatives, and then you just have a switch or a case statement inside that just, if I'm given value 1, I do the first one. If I'm 2, the second one. Obviously, other ways to implement it, but that's it's actually a fairly nice way to do it. And that way you can have the same kind of chunking. That is, maybe your parallel do has 20 arms, but you really only want to devote 4 lightweight threads to it. Then you can essentially chunk these different alternatives as well. Okay, so one of the advantages of doing a syntactic approach is that you, instead of having pragmas, which are sort of, if you say it might call it a menu approach, where you choose this and you choose that, and you sort of layer these things one after another, and you add more and more parameters and so on. With syntax, you can kind of use a building block approach, where you say, well, we've got parallelism, we've got iterators, we've got filters, and so on, and you combine them syntactically to achieve your overall parallel algorithm. So one of the things that Ada started adding in Ada 2012 and continued in Ada 22X is the notion of a generalized iterator. And what you can do with those iterators, you can create an array by embedding an iterator inside the array and generating the elements. So that first array there for I in 1 to n, right arrow A, I star star 2, that says create essentially a table of squares of integers from 1 to n and produce an array. Looks like we lost a right bracket right there. There should be a right bracket there. You can see it if you look very closely. You can also iterate over a container. And for each element of that container, you can turn that into an element of an aggregate or an array. And finally, you can take one of these array-like constructors and then reduce it, giving it some operator and some initial, identity value, and it'll reduce that down to a sum of squares in this case. It doesn't actually create the array, it simply generates the values that would have generated an array and reduces them. So that's just an example of where you can use iterators. now that we see places where you can use iterators, other things you want to do with iterators, you want to provide a filter. That is, I don't want every element. For E of C says for every element E of container C, when E mod 2 equals 1, then generate an element. So that would create an array of the even elements of a container. There's also an iterator for iterating over where you sort of write your own iterator, and it ultimately turns into kind of a, you call a function, in this case iterate, and the iterate function turns around and calls your loop body. So this is a way where you can basically create a loop body, turn it into a little function, essentially a lambda kind of approach, and iterate over it. You can also add a filter there. And finally, when you want to do a reduction, it's quite often where when you're doing the reduction, you don't want to take every element of the container. You want to take the ones that satisfy some restrictions. So in this case, age p greater than 30. So this is just showing you, we've seen iterators, we've seen filters, and now we add the word parallel, and we can put it in various places. When we do put it in, we can always specify the number of chunks we want to break this into, sort of the maximum level of parallelism. And we can even give a name to an individual chunk so that when you're in a particular iteration, you know which chunk you're in, and you can use that to, for example, index into an enclosing array. Here's an example where we iterate over an array, and then we have a chunk index, which allows us to effectively roll our own reduction. We do have this reduce operator, but sometimes you've got more complicated things that are not exactly easy to map into the syntactic reducer. So we can have our own, essentially roll your own reduction. So once we have these building blocks, we can combine them. And that's what makes the syntactic approach interesting compared to, let's say, a pragma approach. We can put in the parallel, we can choose which iterator, we can add a filter, and then the things that we can do with that iterator is we can do a loop body, we can do an aggregate, we can do a reduction, or we can do a quantified expression. You can say for all I in, or for all E of C, I want to know if some element is greater than 10, or et cetera. So essentially you can create a quantifier for all and for some. And in each one of these cases, you can put the word parallel in there to effectively request some parallel execution. So anyway, so how did we fit OpenMP into this picture? Well, as we've heard, OpenMP originally sort of provided kind of heavyweight threading based model, and has evolved more towards this task-based model. And as Michael said, they recommend the task-based model for sort of new language bindings. And I think certainly for Ada, he always felt that was the way to go. And so we followed his suggestions. And we rely, as I was saying, on the Ada syntax for defining the overall parallel algorithm. And then you could still have implementation defined or even standard pragmas, or what we call aspects, which are sort of like attributes in C++, or library calls to do tuning. One of the things I like about this separation is that to some extent, the algorithm, the fundamental parallel algorithm, is in the syntax. And you could pretty much erase all the pragmas and have a perfectly reasonable, meaningful program with, with parallelism. But you could debug your parallel algorithm and not worry anything about any sort of tuning or any kind of target specific thing. And then you can add in tuning, and the tuning is visibly different, if you will, from the algorithm. So I think that's one advantage of embedding sort of the fundamental parallelism in the syntax and preserving the pragmas and aspects and so on for more of the target specific tuning. So how did we make this mapping? Well, there's an OMP parallel directive, which kind of kicks everything off, and it creates a team in general. And then that team can be used to support the OMP tasks. Well, we have the same basic idea, but there's no syntax, there's no special pragma for creating a parallel region. You actually declare an object of type OMP parallel, and you specify when you declare it how many threads you want, how many servers you want, how big the team should be that's going to support this piece of your program. In Ada, we have these heavyweight things called Ada tasks. So for each Ada task, we allow it to decide how big a team it wants within itself. By default, it will have a team of 1, meaning it will just have 1 kernel thread. But if it's going to be doing some some lightweight parallelism, then it would want to create a team of more than 1. And each task can make its own decision. And in Ada, tasks tend to be real time. That is, some have high priorities, low priorities, and so on. And so the team will operate at that priority level. So you have to be careful when you decide to create a team in a high priority task. It may pretty well take over the program. And then for each of the constructs, parallel block, parallel loop, we use sort of the obvious OpenMP tasking, OpenMP task-based constructs. Create tasks. We use a task group to do an automatic wait at the end. And the same thing for a parallel loop. We spawn the tasks asynchronously, and then at the end of the loop, we wait for the tasks using a task group feature. Now, the question was, how do we deal with the fact that we'd like to have multiple potential lightweight threading schedulers? And what we've done is created a layering, where at the very top layer, we have Ada syntax. The next layer down, we have this sort of package called system.parallelism, which provides sort of nice features for the compiler to generate code to. And then that turns around and calls a lower level interface, which we call system.lwt, which is almost one-for-one with OpenMP kinds of directives. And then you plug in a lightweight thread scheduler, which just implements this LWT interface using essentially a dispatch table. So I'll show you what each of these things do, and I'll go through some examples, or an example. So here's an example where we have a parallel loop. And what I mentioned was OMP parallel is how you sort of kick things off. And this is the only piece of OpenMP that I ever have to mention. This is where I'm specifying the size of my team for the main program. The main program is essentially conceptually a task. And so I with interfaces at OpenMP, and that will set up the number of threads that I want.
Just a quick interruption is about 3 minutes out to the 5-minute remaining mark.
Thank you. And then those are translated by the compiler. Essentially, it turns those into, it generates a little loop body for the body of the loop as a separate procedure, and then it calls this par range loop routine, which is part of system.parallelism, and it passes in the loop body as a pointer and the bounds and so on, and then that turns around and expands into calls on a lower level routine to spawn a lightweight thread, and then at the end it waits for the group. And in fact, in this particular example, the lightweight thread spawns the other lightweight threads. So it's sort of a chaining system. And then down in the lightweight thread level, we have a plug-in mechanism where essentially the whatever lightweight thread scheduling you chose gets plugged in to this layer. And finally, we are down here in the part that is in fact now OpenMP specific, and it installs itself, if you will, when it is initialized as the implementer of this lightweight threading system. So I was going to have a demo here, and I'll actually save it for the question and answer period if people have questions relating to it, and I can show you what we can do and how this layering can be. We have two different lightweight threaders. One is OpenMP. Another one is one that was written by hand to do work stealing, and I can illustrate that. Anyway, conclusions, questions. I think this. The advantage of this layered mapping for us is that first, it allows us to accommodate the fact that Ada really cares about safety and security, and it may be that the off-the-shelf lightweight thread scheduler perhaps isn't as worried about that. But also it lets you adopt new versions of OpenMP, adapt to different lightweight thread schedulers, and so on. The syntax carries most of the load for defining the structure of the parallel algorithm. Furthermore, because of that, the compiler does some data race and deadlock checking, which I'll talk about during the panel session at the end of the day. And that checking is largely independent of the lightweight thread scheduler, which is kind of a nice feature. And then pragmas or equivalent are used for fine tuning. And in fact, this notion of chunking is actually built into the syntax because it's so fundamental. And our claim is this makes the program easier to read and understand, independent of the underlying lightweight threading scheduler details. And I would argue this might be a path for other language bindings to OpenMP. We can see that they're starting to use attributes or annotations for C++, but the syntax is not really being affected more than that. I would argue there may be advantages to actually embedding the notion of lightweight threading into the syntax, and then using some kind of a layered mapping to allow you to install, if you will, your own personal lightweight thread scheduler. So with that, I'll take questions. And I haven't looked at the chat, so you'll have to, Richard, could you read the questions? Yes,
please. If you have any questions, throw them in the chat. I think that was a very informative talk. There's kind of a lot to unpack. I think, I mean, more of a less than a question than more of a comment. What I think is interesting here is that, I mean, it's clear that the language syntax itself really allows anything to happen behind the scenes that can accommodate this parallel execution. So you could even imagine in a embedded environment where you might not have something as heavyweight as OpenMP, you can have that runtime really just create kind of maybe a static team of threads to handle the work. And then when you have a much more beefy environment, if you will, if you're running on a blade with like 28 cores, and then you can go to something like OpenMP quite portably. And I think that's the really the fruit of the syntactic approach. I had one kind of question for discussion that I was wondering about generally, is it conceivable, and this kind of leads into what we're going to be talking about tomorrow, but is it conceivable that these parallelism features might get answered in some way in Annex E, which is a distributed systems annex of Ada, where you could have some ideas of even spreading out certain parallel structures out into a distributed model?
Yes. I mean, I think, well, I mean, to some extent, I asked Michael the same question about using this as the basis for distributed computing. I think GPUs, you could imagine, might map to a separate Ada task, which has its own team of GPU threads. So you could imagine an Ada task, which is representing effectively the offload, and then you would treat communication between the Ada tasks as communications between the physical devices. And I think that's an interesting model that is perhaps worth investigating. I'm just here going to try to get a little demo going just so we can you see my screen, by the way?
Yes, looks good.
Okay. So yes, I do think that this is the basis for distributed computing. And in fact, tomorrow in the panel session, I will illustrate a version of these same concepts where instead of saying parallel, you would say distributed. And that seems like, well, that's easy. That solved my problem. The question is, can you actually achieve the same kind of thing? What is the equivalent of OpenMP in the distributed world? And my hope is to some extent to show you that 0MQ and some of its subsystems can be used for that purpose. And I will try to demo something that's using a combination of 0MQ and OpenMP to do a combination of a distributed and parallel computing. Anyway, I was going to show you a little program here, which uses these features. I don't know if you can see there, with interfaces at OpenMP, use interfaces at OpenMP. So that's kind of what I said you had to do if you wanted to get OpenMP to be linked into your program, first of all, and take over control of the lightweight threading. And then right here, I'm specifying how many threads to use and in my team. And if you can read Ada or languages like it, it says if the number of arguments, which is the number of arguments on the command line, is less than 2, then let's use some default number, which is 6. Otherwise, we're going to use the value of that second argument as the number of threads in our team. And
I just, sorry to interrupt, I've got one question from Sarah here.
Okay.
Are you reusing OpenMP runtime libraries to implement the lightweight threads? And if yes, the runtime might induce lots of errors uncheckable at compile time. And if not, then the benefits are limited because everything else has to be re-implemented.
There are, I'm not sure I fully understand the question, but this is using an off-the-shelf OpenMP, but you could use a specialized OpenMP, or you could use a specialized lightweight threader. The program at this point, by withing this package, is what says, okay, that's the particular lightweight threader I want to use. And I could with my own. So long as it implements this LWT interface, anything that implements that interface can be effectively plugged in as your lightweight thread scheduler. Does that answer your question, Sarah? Feel free to unmute at this point. We're into...
Yeah, sorry, maybe it was not clear enough. The point of the question is that if you have to re-implement the aspects of the OpenMP specification you need for the lightweight threading, that you are not benefiting from the work done in the 25 years of OpenMP. Well, you benefit from the programming model, but not from the implementations themselves.
No, this is using it directly. This is not re-implementing it. This is a direct link to the GCC GOMP implementation of OMP.
Okay, that was the point, because I remember that because you sent me the code like 1 year ago, and I was expecting it to be in LLVM, but then I discovered it was with GCC, so I kind of stopped digging into it for a time, for some time. But okay, if you are relying on other runtime libraries, then it is true that hiding OpenMP inside Ada syntax might hide a lot of problems that can arise because of the use of OpenMP, problems regarding safety and other fault tolerance and so on.
It's not hidden. I make the choice to be what I want to use. In this case, I wanted to use the off-the-shelf OpenMP. If I don't want to use it, then can I do another one? And in fact, I will quickly show you, then I'm going to let the next speaker speak. Here is a implementation of the same program. And the only difference is right here with interfaces.workstealing, use interfaces workstealing. And then I have a separate control WS parallel. It takes essentially the same kind of thing, how big a team. It also allowed me to specify some options. There are no other differences in this program. This is otherwise identical. And so this is an NQueens program, and I was just running it using an OpenMP, and you could see it was creating, these are OpenMP threads, forming a team of 6, and then they together help solve this NQueens problem. I can run the exact same program, and instead of OpenMP, I'm going to use this handwritten, if you will, work stealing implementation, and it essentially gives exactly the same results, but it uses a different lightweight thread scheduler. Anyway, so we can take more questions during the break, but at this time I should give up the screen and let Jan give his talk.
Okay, so next up is Jan Verscheld with parallel multiple double precision to solve polynomial systems. Jan Verscheld is a professor with the Department of Mathematics, Statistics, and Computer Science at the University of Illinois at Chicago. His research focuses on the application of polynomial homotopy continuation to scientific and engineering problems. And as part of his work in his field of research, Professor Verscheld has developed the PHCPAC software suite that he will be speaking more about in his talk today, which is mostly written in Ada, and it's nearly 1 million lines of Ada, which is no small feat, and it enjoys extensive use and citations among the academic and engineering communities across a diverse set of specialties and subjects. Please take it away.
Thank you very much. I hope you can hear me. So I'm actually physically in Chicago. So even though it's not where I would perhaps rather be. I'm in my basement. The problem, so let me see if I can now move. I hope you can see my second slide. So this is the outline. So the problem, the general problem is to, when you work with extra precision, you incur a cost and you want to compensate for that cost. I will make that statement more precise in the middle part, and then I will end with some computational experiments, and actually then yet another problem statement. So actually the goal of my talk is more to explain what my problems are. So the computers have gotten really, really fast, but actually we're still stuck with double precision. And if you compute longer and longer, you're going to accumulate more and more round-off. So the round-off itself is already a problem, but there is the distinction between the round-off and the problem that is singular. By using multiple precision, you kind of get away with the round-off, and you can work with looking more at your singularities, actually. There is the general problem statement. I'm actually also interested not only in speed up, but actually in solving problems better. Better here for the context of this talk is more accurate. And if you want to compute more accurately, then we have to compute longer, and naturally parallel computations are very useful. So here are two software libraries that I'm using. So the idea actually of double, double, and multiple floats is actually an old idea, as old as I am, early 70s, late 60s. So I'm using these two software libraries for double precision. And then there is the more recent Campari library. Now you will ask, what is the difference between the two? Obviously, the quad double is restricted to double, double, and quad double, whereas the Campari is more general. But you can also argue, if you look at the source code, that it's actually the opposite. The quad double library is actually offers the user more functionality. It gives you the decimal expansion, it gives you the square root function, it gives you the sine and the cosine. The Campari library is actually much more basic. It provides you with the arithmetical operations. So I mentioned here the 2016, and I probably learned about Campari in 2016, but at that level I could not do much with this. At that time I cannot do much with this. So now I can actually also use the Campari library. Here is a run. So this is actually Ada code. I took the software libraries and I actually hand translated them just for me to understand what it all means. So hand translating code sounds tedious, and why would you do this in these days and age? But I think that there is a real benefit of actually seeing what actually is happening. And here is a test program that I wrote to test the accuracy. So what is a double-double? A double-double is an unevaluated sum of doubles. Triple doubles, you have 3 doubles. But here I did a computation where I know that the exact answer is 8. So we are computing 8 all the time. Now the computer doesn't know this because I let it generate a sequence of random complex numbers, all with norm 1. And the complex numbers themselves are generated to the full precision. So with decadouble, you have 160 decimal places. And here you see how in the past I was actually always using the decimal expansion. But actually decimal expansion may show you 7.99999, and that makes people uncomfortable if you are a little bit rusty on your analysis. So plotting it like this is actually quite nice. So the second highest double actually gives you the error. In the title I write of this slide, error-free transformations, but I actually only realized what it meant when I was doing this experiment. So actually, if you have no representation errors in your answer will show up correctly. So your answer will show up exactly here as 8. And it is the second highest double is the error. Now, this is the nice thing. So here in hand translating code, you look at the code and then you count the number of operations. I was thinking about timings. I will show timings in the end, but we'll not show timings. I will show more actual experiments in the end. But here is just looking at code. If you add up, so the rows in these tables are the add to adding 2 doubles. That costs you 8 double operations. Multiplication takes you more costs, and then it goes on. The positive thing about the double is that the cost overhead is actually very good. I've mentioned complex numbers. I was used to working with complex numbers all the time, and also complex numbers have to be provided in software. So double overhead is just like complex arithmetic, and you get twice that number of decimal places. Now, if you go higher and higher, you see that the cost seems to be cubic. So to have a 10-fold increase in precision, you need actually 1,000 more operations. So your decadouble there is kind of problematic on one core. Now, this is a little bit about the setup. So I have been working on PHCPAC for now since my doctoral dissertation. So I'm somebody who I made my doctoral dissertation in Belgium in '96, and in 2019 I gave a talk there. And the talk was a homotopy continuation for solving polynomial systems, which was almost the same as my dissertation. And I do not think that I will succeed in actually solving polynomial systems. If I had a time machine and go back to that PhD student, I would say now you cannot solve polynomial systems. Now, for the purpose of this talk, Ada works. In the past, I was asked the question, why Ada? Now people do not ask that actually anymore. Now Ada works for multitasking. It is a very large software package. It's research software. If you look at computational research, there are people who are going to publish 1 program per paper. So you write papers, that's why you get rewarded for, and your software is then kind of an appendix, or actually there's no appendix at all there. What I had in mind when I was designing PHCPAC, that I had all my algorithms that I was publishing are also in PHCPAC. So we are still in the paper world, but I believe that in the future, the software will actually define, the main definer of the algorithms. What has changed as well, at the bottom line, you see that I will do my runs on a 44-core workstation, which was provided by an NSF award, which is one of these cross-cutting awards. I work in a mathematics department, mathematics, statistics, and computer science, but the National Science Foundation has actually also realized that software is important, also to people who do research. So I got a big grant in 2014, and that allowed me to actually purchase. They gave me plenty of tons of money, and I actually could purchase a fine workstation. The other thing is we are doing this already for a very long time. In 2010, I wrote a paper with my student where we actually started to using multitasking. It was shortly after I discovered that tasking actually was no longer concurrency, but actually it worked on multi-core processors. I got actually real speed ups with this. Now, I did not mention this here on this slide, but in 2020, there was a paper of one of my users that actually mentions a 16-core run. So this is a long-term project, and it takes a while till my users start to notice and actually really use this. Now, what is my problem? We are running Newton's method all the time. Newton's method does two things. You solve a linear system, and that is linear algebra. I'm not good at linear algebra, but where I can contribute is in the evaluation and differentiation. Our polynomial systems can get as large as they can, as you want them to be. So actually it scales up a lot. We're also working with Newton that we compute power series. So not the Newton, perhaps the Newton that you have seen in calculus where you were studying power series. We actually are doing our arithmetic on power series. And the power series have several coefficients, and they are again multiple doubles. So now I get to my specific motivation. And actually, this is my most technical slide. So in working with power series, I was first working with matrices and linear algebra problems of power series. So with genetics, it's very nice. So with power series, you can divide them. If your leading coefficient in your power series is not 0, then it has an inverse. So all the linear algebra that you do on numbers, you can also do on power series. Now it turns out that this is extremely nice, but if you think about the lower level, it's actually not the way you should look at it. You should look at it as, instead of a matrix of power series, you have a power series where the coefficients are matrices. And now I can, if you see that, you have a block triangular, lower triangular system that you need to solve. And this is where the round off comes in. Suppose that you can solve your first system, your X naught, with almost entire complete accuracy, except for 2 places that you lose. Then you're going to take that solution to the next level. So if you could see the forward going, you're going to solve a next linear system for the X1 in this slide here. And you're going to have using that X naught to update your B1. So your X naught has 2 bad decimal places at the end. You lose again 2 decimal places for the X1. And it continues. So if you have, so this is the dot, dot, dot. If you work with a truncated power series, truncated up to degree 32, you lose 2 decimal places in every spot. You're going to lose 64 decimal places in total. My colleagues, Mark van Baar made a detailed error analysis on this. You can derive circumstances where it's not that bad, but in general, it can be that bad. This is the technical motivation for our loss of accuracy. Now, if you use multiple double precision, if you work with 160 decimal places, then losing 64 decimal places is not a problem anymore. So you get accurate results. So that's the mathematical punchline of the talk, essentially. And now we get to the parallelism. After the 2 talks, so I'm sure that I do not need to explain how to do parallelism in Ada. I kept it also at the very minimum. I'm still using the Ada tasks, so the heavyweight tasks. That's because actually every job is not a matter of seconds, it's a matter of minutes. I'm using the launching of the tasks and the shutting down of the tasks also to do a synchronization. So there is the evaluation and the differentiation that is done first. So that computes all the blocks in that block triangular matrix. And then we use pipelining to solve that block triangular system. So there are all the right-hand sides that need to be updated once you have your first X naught, and that can happen in parallel. If you do this with doubles, your speed up is going to disappear, but with multiple double precision, all the jobs are actually very, very intensive. And the medium grain parallelism for evaluation and differentiation is that every job is concerned with one polynomial, computes all the derivatives, evaluates at the power series. There are finer levels that we have explored. And the coarsest grained parallelism that we did in 2010 was simply, we have many, many solutions. Every task takes care of one solution. So that was the coarsest granularity. So our computational experiments, they run on random data. So on our 44 core workstation, I can scale things. So I kept the 64. And then I took, I looked at the speedups and the efficiencies actually for 2, 4, 8, 16, and 32. I stopped at 40 because that computer is also actually our web server. I have no total control of what happens there, but I look at the wall clock time. The other way where we can scale it is in the power series. So we use the power series to compute approximations of our solution curves. So the higher the degrees we can go, the better accuracy we have also there. So I will not list timings, but I list efficiencies. So that means that we take the speed up and divide it by the number of ADA threads that I'm using. So actually I have, if I say that I'm working with 2 worker threads, I have 1 master thread that launched the threads, and then I have 2 other threads. So actually when I work with 32 worker threads, I have 33 threads running. Here is the plot of the efficiencies. So the horizontal axis shows the number of threads. And then for 2 threads, I have about close to 99%. Sometimes I may actually see some superlinear speed up, 100%. I chose kind of arbitrary colors for the bars, although the red one is kind of the bad one. I didn't check, but most likely even already for 8 and 64, it could already be that the results are not that good. You see that the efficiencies actually go up. So with 32, you still have a 60% efficiency, which means that you have a speed up of 24. Now, going back to the beginning with the operation counts, I actually would need 100-fold speedups, but my computer doesn't have 100 cores. And the next slide actually should be shown in rapid succession. So you can see that if I go from degree 8, 16, 32, that the bars are actually going up. So the speedups actually improve. So even also for double precision. But actually, I'm only starting to trust the results a little bit with triple double. So you notice also that so it works and it is effective. So the nice thing is that things become compute bound. So you really have the benefits of your multiple cores, and the efficiencies improve. However, you also notice the limitations of the medium-grained parallelism. So that means that if I would probably double the number of cores, the efficiency would not be good. That's why I'm actually happy to learn about the features of the new coming ADA that would allow us to take more advantage of implementing real fine-grained parallelism, where in my application I could start to look at monomial evaluation and have that done as one job. I think I spoke a little bit too fast, or perhaps not. I think I have 5 minutes left.
Yep.
Thank you for your attention.
You're right on time. Oh, that's perfect. I got a question here from Tucker. And you kind of touched on this a bit, but I guess really, I think you just answered this, but it's like, what existing Ada language features made your job easier or harder, right? If we can start with that.
The main benefit I like is the compiler, that it slaps me on my fingers when I do something that is not correct. So you have to know that my software has been written over a very long time. And 6 years ago, I was a different person. I do not know anymore what I did 6 years ago. But everything still compiles very well. So as far as the language Ada is concerned, the fact that it is consistent, that I do not have to change everything for something that was written 10 years ago, is really the main benefit. As far as parallelism goes, I had to rewrite my style of coding. So I was used to working with Scratch arrays as local variables. And that is bad. It doesn't make it thread safe. So I learned also to rewrite gradually my software that it becomes thread safe. Everything is, of course, strongly typed. A vector is a vector. It's not just a sequence of numbers. So the fact that the compiler is severe, and when I compile it and it works on one computer, it's also going to work on all other computers. So I have Windows computers, Macs, and Linux workstations. So the code remains consistent. So parallelism on a Mac works just the same as it does on a Windows as it does on a Linux system. So that's the main benefit so far. Yeah.
I think you've definitely echoed my own experience with Ada there. Once it works, it works. Once the compiler accepts it, it tends to just do what you expect. So I got another question here, which is, I also had a question similar to this that Tucker also asked. So I try to combine these on the fly. But so given that we're kind of in a high integrity theme here, and I noticed that, PHCPAC is getting quite a bit of use in engineering and other sort of related research. So the kind of question is, how do you have you tried to validate the results, or is there so Tucker's question specifically, are there any ways to gain confidence in the correctness of HPC computations?
Right. I like that you misspoke HPC. My goal is to bring HPC and PHC. I did not make that quip, but I can do it now. So actually, yes. So there is a lot of effort being done in certification of numerical results. In a way, I'm going a little bit towards that with the error-free transformations. So there is interval arithmetic. Double doubles are a little bit similar to working with interval arithmetic. They are not the same. There are people who are doing interval arithmetic. You noticed I mentioned COSC. COSC stands for computer algebra in scientific computing. So in computer algebra, they are the opposite of numerical analysis. We work with double doubles as soon as we can. In computer algebra, they only work with double doubles if they really, really have to. So they will do symbolic calculation that is exact. And only towards the very end, they may convert to doubles if you want to see the format. So, but the problem with working exact and symbolic is that that does not scale very well. So the trend seems to be more towards using higher precision arithmetic, interval arithmetic, and more trying to certify things at the end. Yes.
Do you think the use of Ada is going to help in that?
Perhaps, I mean, most of my users simply download the executable and they're completely unaware that Ada is under the hood. So that's fine. Well, perhaps not. So sometimes they see a constraint error if I do not catch the errors, which is much better than a segmentation fault or when you get
Exactly.
a throttling. So in a way, when it crashes, actually, I have the exception handlers handling it. So yes, so in that sense, they notice it. Yeah.
Okay, we're almost at the end, at the start of the coffee break, but I just thought, and if anyone has any more questions, feel free to throw those in the chat. But I think it's interesting that the way you've kind of broken out the problem into parallelism with heavyweight tasks. I think there is an argument that you can make sometimes that if you get too fine-grained with the parallelism, you might lose a bit of efficiency. I mean, it goes both ways, but I wonder if you think it would be really ideal to be able to take certain components of the problem, break them into a heavyweight task, and then inside of that task, apply the Ada 22x parallelism features. Like, is that kind of an approach you would probably take? And curious what your thoughts on that might be.
Yeah, so my main experience is that design matters. So for the Power series, I had 3 different implementations. Only the third one with the linearization turned out to be suitable for scaled applications. So in a way, where I see that the influence in my program matters with other softwares is that people often copy my designs. So they may not copy the actual code or use it to compete, but actually the designs are very important. I think the decision whether to go fine-grained or medium-grained is a very important design question, and often is independent of the language, although Ada can work very well at building a reliable prototype. So once you have the design ready, it can be translated to other platforms and other languages, but getting the design ready and getting it correct is the most important thing.
Great,
Thank
awesome,
you very much,
thank
John.
you.
And if there are any other questions, now would be a time just unmute and ask them if you want to. Otherwise, I think we should thank the speaker again, and we will restart at 12:30 with our talk and then our panel. And so you can take your coffee break now and make yourself a nice cup of coffee. But Jan, that was very interesting. I mean, I think it's great that we see both sort of all the abstractions. I mean, being a compiler vendor, I never write HPC programs. I only think about them and test them and write silly test cases. But it's great to have an actual program that is used, by a lot of people and is solving a real problem in terms of. It's interesting when you say you lose 2 digits of precision on each each level. That's sort of saying, wow, that pretty soon there's not much left. But if you say 160 digits, well, okay, then I guess it's not so bad. But it's fascinating to see how you've accomplished so much. And I am hoping that our parallel features will make it even easier to do some sort of finer grained parallelism without having to restructure everything. So thank you very much.
Thank you.
Just wanted to quickly check. Can anyone hear me?
I can hear you.
Great.
Can you see this slide that I'm showing?
I can see that slide, yeah. Should I share my screen for this?
Yes, when you're ready. Why don't you wait until maybe a minute or two after. I'll introduce you, and then I'll stop my sharing, and you can take it away.
All right, sounds great. Thanks.
Yeah.
How have you been doing?
Good. I spent the summer on Martha's Vineyard. That's a picture of where I spent my summer, which was very nice.
Very nice, yeah.
Now I'm back in Lexington and doing okay. You know, I guess that's an advantage of our field. We can do most of what we need to do without actually driving anywhere or
Yeah, definitely.
physically going anyplace. So yeah, I'm going to be presenting my newest work on distributed computing tomorrow. So I'm kind of excited about that.
Cool. Sounds great. Best of luck.
Thank you. So I'll give it a minute or two and then introduce you, and you can take it away.
Sounds great. Thanks.
So I want to welcome people back from their coffee break or lunch if you can eat really fast, or dinner, I suppose. It really depends on where you are. And I think we have someone from New Zealand. So for him, it's an early breakfast probably. Anyway, so our next talk is about using the Taper compiler intermediate representation to support efficient parallel languages. Good title, pretty much says it all. Our speaker is TB Shartle, who's at MIT CSAIL, which is the Computer Science Artificial Intelligence Laboratory. I met TB just in the last year. I gave a talk over at CSAIL, and he and I got to chatting, and we had a lot of interesting things to talk about, and he seemed like an ideal person to address this very interesting issue of how can we make parallelism more mainstream in our compilers, as well as through things like the OpenMP library and so on. We have to kind of get a little bit more intelligence into the compiler. As you can see that TB has been working in this area for a while, and this is related to LLVM. Taper is essentially, I think, a variant of LLVM, and the goal is to without totally rebuilding LLVM, insert enough visibility on parallelism that it can actually do some pretty interesting optimizations. So with that, I will stop sharing, and I'll let TB share his screen.
Great. Thank you for the introduction.
Certainly.
All right. So you should be able to see the slides.
Yes.
And hear me all right?
Yep.
Okay, so I'll go ahead and get started. Thank you everyone for coming to this talk. I'm TB Shartle, and today I want to talk about the Taper compiler intermediate representation and how to use Taper to support efficient parallel languages. Now to start, I want to tell you a bit about Taper, and to do that, I want to show you an example of the kind of problem that Taper aims to solve. So in this example, what we have is a very simple piece of code which consists of a simple loop where all the loop iterations are completely independent. And this is a loop that's trivial to parallelize. And lots of languages today offer simple parallel linguistic constructs that make it easy to transform this code into a parallel implementation using something like a parallel loop construct. Here, we're just using Silk 4 to implement that parallel loop and allow all the iterations to execute in parallel on whatever parallel processing resources happen to be available. But when we parallelize this code, we quickly encounter a fairly disastrous problem. What we see is that whereas the original running time of the serial code was about 0.3 seconds, the running time of this code on 18 cores is now roughly 3 minutes, or approximately 600 times slower than the original serial code. And if we actually run this parallel code on just one processor, we find that it's roughly 8,000 times slower than the original serial code. Tucker mentioned before that we want to use parallelism in order to speed things up. That clearly didn't happen in this case. What went wrong? Well, as the title of this talk suggests, the problem in this case lies in the compiler itself. So let me quickly overview how a modern compiler such as LLVM works at a very high level. And essentially, LLVM works by processing code through a pipeline of stages. You start off with language-specific software that gets processed by some language-specific front end, whether that's Clang or a variant of Clang to support different parallel extensions. And those front ends all translate the code down into a common intermediate representation known as LLVM-IR. That LLVM-IR gets analyzed and optimized through some middle-end optimizer. And then that optimized LLVM-IR goes through some architecture-specific code generation phase called a backend to generate machine code for some target architecture. Now that's a high-level overview which applies to serial code, but it turns out that when we compile parallel language constructs today through such a compiler, essentially it's the front end that handles all of the parallel language constructs. So what exactly do I mean by that? Well, if we take a look at our example again, and we see, roughly speaking, what comes out of the front end when we compile this code, we see that whereas we had a simple parallel for loop at the beginning, in the LLVM-IR representation, we just have a mess. Instead of a parallel loop, we now have a call to some runtime method that executes the parallel loop, but the compiler basically knows nothing about. That runtime method takes a pointer to some other compiler-generated helper function. And in that helper function, that's where we actually have the loop body. But the problem here is that the code is now so obfuscated that the compiler really has no chance of being able to analyze and optimize this code effectively and do things like realize that it could hoist this call to norm outside of the parallel loop and dramatically improve performance that way. Okay, so this is a big problem and it costs us a lot of performance. How do we solve this? Well, one simple idea is to say, well, let's just teach the compiler something about parallelism. Let's just embed parallelism directly into the intermediate representation of the compiler. Turns out that this is a pretty old idea, and it's an idea that has been explored by lots and lots of people over multiple decades, both in academia and industry. This list on the slide is by no means meant to be an exhaustive list of all previous attempts at embedding parallelism into the compiler. It's just meant to illustrate just the breadth of approaches that people have taken to try to address this problem at the compiler level. And so when we decided to take on this problem, we actually asked for a little bit of advice from some of the people who've worked on this, and they were able to convey some of the wisdom that they've garnered over decades of work on this topic. And the advice looked something like this. Introducing parallelism into a so far sequential IR will cause severe breakage and headaches. Parallelism is invasive by nature and would have to influence most optimizations. It is not an easy problem. Defining a parallel IR with first-class parallelism is a research topic. And this kind of feedback goes on and on. Essentially, the folk wisdom that have been developed over all these years is that if you want to teach the compiler something about parallelism, you're really talking about rewriting the whole compiler. And compilers are big and complicated code bases. So in general, rewriting a compiler is a non-starter. Now, what we managed to do is develop an intermediate representation, which we call taper, ostensibly short for task parallel IR. And taper has some remarkable properties. It embeds parallelism into the IR of the compiler, but it does so just by adding 3 instructions to LLVM's intermediate representation that together encode recursive fork join parallelism. And they have this cool property that only minor changes to LLVM's existing optimizations and analyses are required in order to get those passes inside of LLVM to actually work on parallel code. So let me just say a little bit about what I mean by minor changes. We've done various breakdowns over time of how many lines of code do we have to add or modify to different components of LLVM in order to implement Taper. And for the sake of time, I won't go through all the details on this slide, but I want to call your attention just to the first line in this table, which shows that to embed parallelism into the core middle end functionality of LLVM 6, we only had to add or modify roughly 3,000 lines of LLVM 6's 500,000 line code base. So 3,000 lines is not a small amount of code, but it is far from a complete rewrite of the entire LLVM compiler. It's a relatively minor change to LLVM. And what do we get from this change? Well, if we come back to our original example and we compile this with Taper, now we see that the code runs very efficiently on one processor. And now we actually get parallel speedup when we apply more parallel processing cores, which is exactly what we want from parallel computing. But this benefit isn't confined to just one simple example that fits on a slide. In fact, we've tried out Taper on a whole bunch of different benchmarks over time. Here we have the results from 35 different Silk benchmark applications. And what we find is that on 30 of these 35 benchmarks, Taper actually improves both the work efficiency and the parallel speedup of the benchmark. On 12 of them, it improves work efficiency by a substantial margin, over 5%. And moreover, on roughly 2/3 of the benchmarks, Taper is able to achieve nearly ideal work efficiency, 99% work efficiency. Whereas I think the original compiler was only able to do so on 11 of these benchmarks. Now, since we did the original Taper work, we've since experimented with Taper in other contexts. One thing that we did was we tried integrating Taper into a more sophisticated compiler pipeline, namely the Accelerated Linear Algebra, or XLA compiler, inside of Google's TensorFlow machine learning framework. And at a high level, what this involved was modifying the high-level component of the XLA compiler to generate Taper. And for this example, we only focused on the CPU backend just to get started. And it turns out that by modifying it to emit Taper, we were able to simplify that high-level compiler in the process. And then we, of course, feed that Taper representation along with parallel linear algebra kernels directly into Taper to let that Taper LLVM compiler analyze and optimize the code. And what we find is that on a bunch of machine learning applications across different CPU architectures, integrating Taper into XLA allowed us to achieve 30 to 100% geometric mean multiplicative speedups compared to the vanilla XLA compiler. And this is a pretty dramatic improvement. In general, these days, compilers are at the state where if you can improve performance by 5%, that's a huge win. So a 30 to 100% performance improvement due to a compiler change is really outstanding. So today, I want to tell you a little bit more about what this Taper extension to LLVMR actually looks like. And then I'll say a little bit about debugging Taper, and that'll touch on some of the integrity concerns. And finally, if there's some time permitting, I'll wrap up by talking a bit about Taper's optimization strategy. So let's get right into it. To show you Taper itself and how that extends the LLVM intermediate representation, we need a little bit of background on what LLVM itself looks like. Now, LLVM at a high level represents every function in a program using what's called a control flow graph, or a CFG. And in a control flow graph, we have nodes which are basic blocks. These basic blocks contain sequences of straight line code, and they have the property that control only flows into the beginning of the basic block, the very first instruction in the basic block. It flows straight through all of those lines of code, and it only exits from the very last instruction in the basic block. Now, that last instruction could do various forms of branching or return, and those branches will induce edges in our control flow graph, which are known as control flow edges, thereby giving us this graph. Now, like I said before, Taper expresses recursive fork join parallelism, and just let me quickly recap what that means. Recursive fork join parallelism is this model of parallelism that grants permission for parallel execution rather than demanding it. And there are various examples of recursive fork join parallelism that you can find in the wild today. Here's a simple example based on Silk. And we're using the spawn and sync keywords in Silk. And what these keywords mean, spawn allows a function call to execute in parallel with the parent caller, and sync complements the spawn by saying that control cannot pass this point until the spawn children have returned. And notice I'm always talking about granting permission for parallel execution rather than demanding it. The idea with this model of parallelism is that some other runtime system scheduler can actually make the decisions about what code to actually execute in parallel, allowing it to schedule and load balance the code effectively. So Taper represents this model of parallelism in LVMIR by adding just 3 instructions to LVM's intermediate representation. Those instructions happen to be detach, reattach, and sync. And here on the slide, I have a simple example of a Taper CFG. And I don't want to get into too many details of what detach and reattach and sync specifically mean, but at a very high level, what these structures let you do is perturb the control flow graph structure a little bit in order to express that certain basic blocks are allowed to execute in parallel with others, and then to perform synchronization. And the cool thing about Taper is that you get this property that a Taper control flow graph very closely resembles the control flow graphs for ordinary serial code. And they resemble it in a way that facilitates analysis and optimization of Taper control flow graphs as simple changes to existing analyses and optimizations for serial code. We can see that even more prominently if we take a look at parallel loops in this Taper representation. So here we have the parallel loop from before, and that turns into a control flow graph, which is similar in many ways to the control flow graph for an ordinary serial loop, except that we have these detach and reattach instructions that allow the body of the loop to execute in parallel. And like I said before, this representation makes it easy to adapt optimizations that work on serial loops to handle parallel loops as well. Now, those are low-level details of what Taper looks like in terms of the intermediate representation. But stepping back a bit and looking at the overall compiler pipeline, all the examples I've shown you thus far have been based on Silk. But in fact, Taper is an intermediate representation. And we could slot it in place of LVMIR and that compiler pipeline we showed before in order to support other parallel languages and other parallel runtime systems and hardware architectures. And roughly what that looks like is that you can imagine different language front ends would be able to target Taper rather than having to directly manage lower level runtime calls. And then at the back end part, different backends would be able to translate Taper to target different parallel runtime systems or even different hardware architectures. And we've already seen a little bit of evidence of people using Taper in this way. One through the Taper XLA work I mentioned before, but in fact, several other groups outside of our group at MIT have experimented with applying Taper in other areas of parallel computing. There's been some work to extend Halide and Poly to incorporate Taper to do optimizations on parallel code. Some folks out of Los Alamos and Sandia National Labs have developed prototype front end and back ends to Taper to handle OpenMP tasks. There's been some work in a different research group at MIT that's explored extensions to Taper to compile programs to the swarm architecture that they are developing. Some work out of Simon Fraser University developed Tapas, which is a high-level hardware synthesis tool that builds on top of Taper in order to synthesize parallel accelerators for recursive fork join programs. There's ongoing work that I've actually gotten involved with on integrating Taper into the Julia language. And there's a company in New York City called Lucada, which has actually developed a backend to Taper that targets their custom in-memory processing architecture. So that's a bit of an overview of Taper itself. I now want to turn my attention to a rather interesting question about what did it take to debug Taper? And because Taper is all about parallel programming, debugging Taper really focuses on the question of race bugs. If you've done any parallel programming, you're familiar with race bugs almost certainly by this point. And race bugs really threaten program correctness and integrity in a manner that's unique to parallel programs. You don't get race bugs in the same way out of serial programs. On the slide, we have a simple example of a race bug, and we just see the flavor of a race bug here, where we've got concurrent updates happening to some shared variable. And what happens when we run this code in parallel is that those updates may occur in any order, and some updates may in fact be lost, causing this code to potentially behave non-deterministically. Race bugs are kind of the bane of any parallel programmer's existence. It's easy to spot a race bug in this 6-line example, especially given the slide is pointing at the race bug very specifically. But if you expand this code example to a 1,000,000-line code base, how do you expect to find those race bugs in general? The other thing about race bugs that makes them particularly pernicious is that they can behave non-deterministically. And so you could run the program many, many times and just get lucky and never actually see different results, which means you might not even know that the race bug is there. Now, those are standard problems when it comes to writing parallel code. When we start working on a parallel compiler, we have a new problem, namely, it could be the compiler's fault. What if it's the compiler that accidentally introduced the race? And this is essentially a compiler writer's worst nightmare, because I can imagine that I'm working on this multi-million-line code base that is LLVM, and along comes some issue in the issue tracker with some disgruntled programmer saying that they wrote race-free code, but the compiler, put a race in it. So I might download this code and run it 1 or 10 or 100 or 1,000 times and possibly never see a problem. I might see that the code runs perfectly every single time. And now, as a compiler writer, I'm stuck because I don't know whether the compiler really is buggy or perhaps the programmer is just wrong and made some other mistake. Now, a lot of work has gone into traditional race detectors, and one could ask, can we just use some of those race detectors like Fast Track or Thread Sanitizer to find these races for us? It's important. There are a couple important things to note here. These race detectors are actually best effort, meaning that they are not guaranteed to find a race in a program if a race exists. They require some kind of scheduling of the program that exhibits the race in order to be able to report the existence of the race. In addition, these race detectors are really designed to handle just a few parallel threads, roughly comparable to the number of processors on the system. And that recursive fork join parallelism model I described before, it's really designed to get parallel speed up by exposing a lot more parallel tasks than processors, orders of magnitude more parallel tasks than processors. Now, the good news is that for Taper, there actually is a race detector we can use. The Taper LLVM compiler itself incorporates SilkSand, which is a provably good non-determinism detector, as we call it, for recursive fork join programs that can verify the existence of a race bug deterministically. In particular, what SilkSand does is that if you give it a program and an input, in other words, a regression test, it's guaranteed to either find a race in that program if one exists, or certify that no races exist. In particular, there is no need for SilkSand to have a specific schedule that exhibits the race. It can discover the race deterministically, regardless of how scheduling might occur. Furthermore, SilkSand's algorithm is efficient. It's approximately constant overhead. And we've in fact used SilkSand pretty extensively when developing both Taper LLVM as well as Taper XLA later on in order to pinpoint optimizations within the LLVM code base that were introducing races. Now, I don't have time to get into a lot of the nitty-gritty details of how this works, but just to show you a little bit of the secret sauce. The reason this all works comes back to this notion I alluded to before, that Taper CFGs really closely imitate the control flow graph of an ordinary serial program. And we can actually formalize that by saying that a Taper models a parallel program's serial projection. Intuitively, the serial projection is a serial program you get from a simple syntactic transformation on the original Taper program. And that serial program actually encodes one of the valid executions of the original parallel program. And because Taper programs have this serial projection, this notion of a serial projection, at a high level, that really simplifies reasoning about program correctness, both statically as well as dynamically. So that's just a little bit of the flavor as to why we're able to effectively find race issues inside of the Taper compiler and debug them. Now I have just a little bit of time left, so I will tell you a little bit about Taper's optimization strategy. And to do that, I want to come back to that original example where we were normalizing a vector, but this time take a look at the OpenMP case, because it's a bit interesting and revealing. When we parallelize the normalized code using OpenMP, what we discover, even with an ordinary compiler like LLVM4, when we run this code on one processor, we actually get good work efficiency. The serial running time is pretty close to the running time of the original serial code. The parallel running time is frankly a bit disappointing, but it's strange that we're able to see great work efficiency in this case without Taper. So what's going on here? Well, to see what happened, we're both going to have to dive into the compiler a little bit, as well as do a little bit of math. So let's first take a step back and look at that normalized code, but just the serial version of it. So let's ignore the parallel constructs for a second. In this normalized code, we've got this norm routine, which computes the norm of a vector in linear time. And if we look at the normalized code as it's written, that loop calls the norm routine n times, which means that the overall running time is quadratic. But that's all before compiler optimization. After compiler optimization, the compiler is clever enough to move the call to norm outside of the loop and just use a stored temporary containing the norm of the vector inside of the loop. And after that transformation, the resulting code now runs in linear time. But that's the story with serial code. What about parallel code? Well, now let's dive into the compiler. When a normal compiler today compiles this OpenMP code and optimizes it, what we get is actually pretty similar to what we saw before, where in place of the parallel loop in our original program, we now have a call to some runtime method, kmpc4 call. That runtime method takes a pointer to a compiler-generated helper function, OMP outlined. That function happens to be run once per processor. But if we dive into OMP outlined, what we find is we've actually got a version of the original loop, which just does a fraction of the iterations, but it does them serially. So this helper function actually contains a serial copy of the original loop, and the optimizations are able to optimize that serial copy inside of OpenMP outlined. They're not, however, able to move the call to norm completely outside of the parallel loop. And so what's the ramification of this? Well, let's analyze this OpenMP code. Once again, our norm call runs in linear time. And if we take a look at just the OMP outlined helper function, we discover that we're doing a call to norm plus some local fraction of the iterations, but the overall running time of that function is still order n. And like I said before, OMP outlined gets run once per processor. And so the overall running time of this code is actually n times p, where p is the number of processors. And if we think about this, this is kind of terrible, because it means that this code is actually only efficient if you run it on one processor. And as you scale up the number of processors that you use to run this code, the amount of work that it's doing is going to scale proportionally. So it's actually mathematically impossible for this code to get more than a minimal amount of parallel speedup. And that's going to be true even if you try things like parallelizing the norm routine. And of course, if OpenMP doesn't have full control over the processors, this code could exhibit slowdowns.
Up now, please, so we can have some time for
sure thing.
questions.
Two more slides.
Okay.
This example inspired the optimization principle underlying Taper, which is the work first principle. And basically what that says is that Taper first strives to optimize the work of the computation, the total amount of computation, rather than the parallel execution. And then it'll sacrifice just a minimal amount of work in order to support parallel execution. And this principle at a high level ensures that parallel codes compiled with Taper are fast on a variety of systems and runtime environments. So just to wrap up quickly, with a quick overview of the status of Taper, this work was originally published in PPOP back in 2017, where it won a Best Paper Award. We're continuing to maintain and enhance Taper as part of the ongoing OpenSilk project. And we actually invite you to try Taper LLVM yourself. We recently released the third beta release of OpenSilk, which you can find at opensilk.org. And that includes both a hardened version of the Taper LLVM compiler, as well as several productivity tools, including the SilkSand race detector and a scalability analyzer called SilkScale. And OpenSilk at this point has been battle tested by hundreds of undergraduates and graduate students at various universities. So that's why I wanted to tell you about Taper today. Be delighted to take any questions.
Thank you very much. I've come up with a few questions, but we also welcome them from the audience. But I'll start with the ones that I came up with, and hopefully there'll be others added to the chat. Feel free to add some to the chat. Well, here's a new question. Can Taper support mechanisms other than fork join, such as futures?
Can Taper support other mechanisms beyond fork join? So right now, we have focused on fork join parallelism for Taper. We're looking at research that's been done in the community concerning futures, and we've thought a bit about what ways we might extend Taper to support such mechanisms, but that's still a research topic.
Is silksand strictly a dynamic data race checker, or does it do anything via static analysis?
Ooh, good question. So silksand itself is a dynamic race detection tool. And it's a dynamic tool in order to provide precision. It'll never report false positives, and it'll never report false negatives. That being said, one of the things that the compiler actually does is some amount of static race detection in order to speed up silksand's dynamic checks. So it's actually able to use the parallel structure of a Taper CFG to find places where a race might occur. So in fact, we're able to do some amount of static race detection using Taper. And we're right now using that to facilitate and to speed up the performance of silksand. And so there is in fact a bit of both in play, if that makes some sense.
Sure. And one last pair of questions. How does Taper relate to GCC? Any chance it's going to show up in the GCC world? And also MLIR, which seems to be also another, not similar, but it's obviously in the LLVM space.
Yeah, so let me talk about GCC first. We chose to do our implementation of Taper based on LLVM, in part due to the expertise we had available. LLVM I've only dabbled a bit in hacking on GCC, and that was a long time ago. In general, GCC also represents code using a control flow graph representation. And so there's nothing fundamental stopping someone from adding Taper to GCC. We just simply haven't had the resources on our end to do so. But the design that I've described so far of Taper as this slight perturbation to the CFG could be done in other mainstream compilers, including GCC. We've also looked at how Taper might relate to MLIR. That is ongoing research, but just to tease a little bit of what we found, it's both encouraging and I find it a little discouraging. So on the one hand, MLIR, I'm not sure how much familiarity this audience has with MLIR, but basically MLIR lets you build intermediate representations. And one could imagine using MLIR to build an intermediate representation, including Taper. And in fact, from talking to the MLIR community, that would be a very, very easy thing to do. The thing is, if you were to build an MLIR dialect, as they're called, that incorporates Taper, you would get all the benefits of Taper through MLIR, namely optimizations on MLIR written for serial code would work with minimal modification for Taper code. Problem is that MLIR is still very young, and there aren't really any optimizations written that target MLIR, at least last I checked. And so that claim kind of holds vacuously. So
okay, well, we should probably let the next panel start. But
sure
I want to thank the audience and thank the speaker. It was very interesting.
Thank you very much.
And now we're going to let Sarah, but I think Richard, do you want to, who's going to introduce?
Just a quick intro. So I'll leave it as much as I can to Sarah. So now we're going into our first panel, which is on moving responsibility from users to vendors when it comes to things like using OpenMP in high integrity systems. So Sarah is a postdoctoral researcher in the computer science department at the Barcelona Supercomputer Center. and she's been specializing in high performance computing for 10 years now, and also has a strong background in real-time system. She has a vast experience in compilers and analysis tools for enhancing performance, scalability, and usability of parallel programming models. So great person to introduce this talk this afternoon. Thank you. Take it away.
Thank you so much for the introduction, and thank you everybody for being here. So I hope the discussion is very interesting for all of us. So you did already introduce me. I'm really happy to bring this conversation to this workshop because it fits perfectly on the topic, and it allows us to gather important actors from different domains that can give us a lot of information on this topic. So overall, just to introduce a little bit the panel, the use of parallel programming models has become a necessity, even in real-time systems. But parallel frameworks are a relevant part in the software stack because they allow implementing the advanced functionalities that are required in the modern societies, on top of the complex heterogeneous architectures that are required to meet the requirements of the systems. So particularly, we are interested in OpenMP, which is a parallel API traditionally focused on HPC, but that includes several interesting features that can be applied to safety critical systems. And these include the tasking model, the accelerator model, and several directives that were introduced early this afternoon by Michael. So these characteristics have drawn the attention of many players in the critical domain. Nonetheless, there is still a gap to be filled because, as he said earlier, Michael, and I think that the specification of OpenMP has changed slightly. So the phrase I put in the panel might not be the same exactly that we have in the latest specification, but the idea behind is the same, is that the responsibility of doing correct programs is not on the API, is not on the compiler or the runtime, but it is on the programmer. So although this is acceptable in high performance computing, it is not in high integrity systems. So that said, OpenMP this is a small but fundamental part in the OpenMP programming model, but it is a showstopper on the introduction of the language in the systems we are interested in. So we want the opinion of the panelists that we have today, which are technical leaders in diverse domains, and I will leave them, they will do the presentation themselves. So I hope all of them are here. I didn't check, but if you wanna go, Dirk, Michael, Tucker, and Eduardo, please introduce yourselves and maybe make a statement of your position regarding the panel, and then we will go into the details of each of the sections. Thank you. Dirk?
So thanks, Sarah, for introducing the panel. And yeah, my name is Dirk Ziegenbein. I'm from Bosch Corporate Research in Renning, close to Stuttgart in Germany. And well, Bosch is one of the leading suppliers of cyber physical systems in the world and the largest automotive supplier. And so for us, it's when looking currently at what's going on in the automotive domain, then we see that we have the trends of automated driving and also the centralization of electronic control units to powerful vehicle computers. And we see a really dramatic increase required in required performance for building those systems. And to me, it's one of the most demanding design endeavors that we currently have in cyber physical systems industry. So I mean, you integrate really different applications with multiple levels of criticality, criticality in terms of real time and safety, onto one platform, which is a heterogeneous platform with accelerators, multiple cores. You have very interesting real-time interference effects between the cores due to, and also the accelerator, since they all share the interconnect and the DRAM. And you have lots of flexibility, which is required also in the software stack. So you have middlewares, software-defined networking, upgrades, updates, and so on. And you do all this in a distributed development fashion. So with multiple suppliers, the car manufacturers all working together on such a system. And basically what it ends up is you have lots of sophisticated configuration of the underlying hardware software platform. And really, if you want to build an application on top of that, you need some sort of abstraction to hide this complexity from the guys who actually want to develop the application. And so this is something that brings, the need for a programming model or models of computation that you're able to actually build such systems. And we faced as an industry this, so something like in 2013-14 with the migration from single to multi-core microcontrollers, we faced also something there. We went kind of like to the research community, found the concept of logical execution time paradigm to decouple the function developers from the system integrators. And for vehicle computers, we're not there yet. So, I mean, the applications are more diverse. It's not so easy to do this. And this is why we engage in research projects like, for example, Ampere together with Edu and Sarah, where we, for example, intend to explore also OpenMP for automotive systems. And maybe regarding this statement that OpenMP says the application developer is responsible for correct functioning. I mean, in the end, the final responsibility always lies with the company that brings the product into the market. And so in that sense, also if you're writing a C program, you have to have some sort of guarantees from the tooling or need to qualify that. And we'll come to that probably later also in the panel. So this is for me not a fundamental showstopper, but of course there are things to be done by the vendors of compilers and runtimes. So thanks, Sarah.
Thank you, Dirk. Michael?
All right, I was expecting to go in alphabetical order, but anyways, so I mean, I covered FUSA in real time in like 2 minutes in the keynote today. The thing I want to say though is, I mean, I'm biased towards OpenMP, so I consider OpenMP as a cool programming language for parallel applications. One of the things, as I noted in the keynote also, was that, or is that, OpenMP is geared towards high performance, yet it's a very expressive programming model. So you can go from this high-level descriptive parallelism to very prescriptive exposure of control, what the implementation has to do. This is one of the potential benefits because, given the volume that car manufacturers or manufacturers of embedded systems in general are facing, every cent that you can save, and money translates to performance that you can extract from the available ICUs. So in this space, performance is irrelevant because the computational problems that have to be solved in those embedded systems are really tough ones. They're not so far away from what other people are doing in HPC on a bigger scale. Just it's now running inside a car or inside a drone or whatever embedded system. So high performance is very critical to those domains as well. The one thing I can say is that the OpenMP ARB, as Sarah and Edu most certainly know, is highly interested in this domain, and we are welcoming feedback as well as proposal how to extend, subset, or however you want to modify the OpenMP feature set, both in terms of syntax and semantics. It's clear that OpenMP is not suited for FUSA, right? The lack of a true error model and the sentence that Sarah was quoting, and that was I was repeating in the keynote, kind of makes it hard to have resilience and error-proof execution in OpenMP. Even though a potential implementation might exploit the undefined behavior to do something useful, right? Because we are geared so much for performance, we usually just don't do it in real implementations like Clangs or Intels or even GCCs. So the assumes directive that we put in might be a first good step into the right direction, saying, you may now assume as a compiler or implementation a certain context or a certain property of the code, but that's certainly not where we want to be or where we need to be to make OpenMP a successful programming model in that space. That's it.
Thank you, Michael. Tucker, you wanna go?
So I'm going to share one picture.
Sure.
So this was from my earlier talk, but our goals for Eta22X was to make it easy and safe to write parallel algorithms. And by safe, we mean both in the sort of minimal sense of my program won't crash, but also in the more serious sense of being certifiable in some sense, that it will not do certain things and it will do other things and so on. And I believe that does mean that the compiler has to work harder. And one of the advantages of having some syntax is then you can also have, you can associate various compiler level rules with those, legality rules and so on. And I'll talk about that more when we come up to tool support. But I guess we have tried to use OpenMP as one way to achieve some of this lightweight parallelism. But as I mentioned in my earlier talk, the intent is to be able to replace that if necessary to achieve the levels of certification you need, while using a model that can accommodate both OpenMP and other things. Sarah asked about, it sounds like you're maybe getting the worst of both worlds because you've got this very complex model, and if you want to replace it, you've got to re-implement the whole thing. In fact, the model that we require is very simple, and it's limited to the task side of OpenMP. So I think that would be one example of a subsetting you could start from. And even there, we're not trying to support every nook and cranny. And our expectation is that if you do have a full OpenMP and underneath that, you've got other ways of controlling it. But if you want to just have the basic, let's say a basic work stealing model and not a lot of other bells and whistles, that's something you can do. And I was just checking that our implementation for such a simplified work stealing model is 2,500 lines of Ada code. So that's a much more manageable amount of code in terms of certifying for safety.
Thank you, Tucker. So last but not least, Edu, you want to go?
Thank you, Sarah. My name is Eduardo. I'm from the Barcelona Supercomputing Center. And I've been digging into the OpenMP world and trying to match or trying to bring OpenMP to the embedded domain. And what I realized in these 3-4 years that we have been trying to push is that there are different needs or different understandings of what people consider as a high-level programming model. And I think here we have the 3 very good examples. Because Dirk, in fact, and I think that Dirk really does not care about OpenMP in the sense of the language per se, but he cares about some abstraction that can be portable across multiple art forms that can express the parallelism, so you can exploit all the performance of these platforms. And OpenMP is one of those, I think. So Dirk is most likely at the, and then of course we can discuss this during a panel, but it's more, let's say, at the system level, understanding that the different components, the different functionalities of the car operates as it should. And of course, then when you are entering within one of these functionalities, then there you can really optimize this with OpenMP or CUDA or OpenACC or OpenCL or whatever it is. But really, Dirk, it's really, let's say, at the highest level. Okay. Then at Aker is somehow in between. Is okay. Ada still we are programming. We want to describe the control flow, and we want to describe tasks. But that's it. So we don't really want the programmer to be responsible of saying what data is shared, what data is first private, you know, the different dependencies existing among different tasks. And this needs to be as much as possible controlled by the compiler. And then you have ICL, that it's at the bottom part. Like, you know, I want to have full control of everything. I want to be able to say this variable is shared and this variable is first private, because then I can make an efficient use of the memory, right? And exactly what we need to do, right? Try to reconcile this. Dirk can describe the system, their CPS system using the modeling languages they are using. This can run on top of Ada or on top of C, but this execution model that Dirk is defining needs to be consistent with the one Tucker is defining at the Ada, but also compatible with what they want underneath. That at the end are the programming models that are supported by vendors. Right, because if you buy an I don't know, an NVIDIA board or an Intel board or a Texas Instrument board, they will support OpenCL, OpenMP, whatever programming model, right? And this is what we need to be able to link this. And here, the one I'm very interested in is to make this parallel programming model supported across multiple platforms is OpenMP. And then we can build the different abstraction levels on top of this.
Thank you, Edu. That was actually your introduction and a nice wrap up of what all the actors in here do. And actually, I just want to add that you pointed out the differences, and I was writing down the similarities, because I'm very happy that all of you mentioned the complexity and the easiness and the descriptive behavior instead of prescriptive behavior. So it is true that all of you have a different view of what it is, but all of you agree on that it has to be easy, right? So let's move now to the first section that will talk about requirements. I want you to discuss about the requirements and in high integrity and safety critical systems, because the definition of the requirements is one of the most important parts in the safety critical domain, and particular cyber physical systems as well. And not only regarding functionalities, which of course, but also considering the non-functional requirements, no? The performance, the power consumption, stuff related to safety, like reliability, etc. So, as you said, Edu, at the higher level, we have maybe techniques like model-driven engineering that are very useful for formal verification, but might not be adapted enough for expressing parallelism. So I want to start the discussion in this direction, maybe with Dirk, because it is your scope. So about the tools that we have available for guaranteeing requirements at this higher level of the software stack, and what do they express, and how this can be pushed to the bottom of the software stack. So Dirk.
Okay, so maybe one comment to this highest level. So for us, really, it's very important to be able to describe the behavior really in a deterministic and portable way. And so this is really this decoupling aspect. Yeah, so that we do not really, for the guys who do the function development, do not really need to know the details of what's below. You know, they need to have an easy, understandable model that is matching their problem domain. Yeah, so for example, this logical execution time abstraction was really nice because it was for those guys very easy, because they were thinking anyhow in time triggered periodic systems, like coming from control system, and then having a fixed latency like the logical execution time. It was for them very easy to relate. Also the multi-rate transitioning was very clear and defined, deterministic, perfect. They could really develop and simulate their functionality independent of the deployment. And this is something which also then helps you really in validating your requirements, at least the functional ones. So, because I mean, you asked for tool support for verifying requirements. Lots of the work in automotive is simulation driven. So it's not so much a formal verification work, but it needs to be like a little bit formally grounded, so that you can hold arguments that what you see in simulation is also realistic in the final system, and that of course then imposes requirements on the tooling when transforming and implementing, going down the levels all the way down to the implementation. And Sarah, you also mentioned it, really something which is really important, the easiness or and the productivity. So there's really this thing that we need to automate whatever is not creative and whatever is possible to automate. And regarding the programming itself, often so much it's not that we can actually change individual functional components because they are legacy software, and we are rather taking over their stuff from previous generations, and we also need to integrate this. So typically it's not the fine-grained parallelism that we're looking at. It's more the parallelism on, let's say, task or core level. And this is, yeah, maybe this gives a little bit answer to your question now.
Do any of the other panelists want to comment on this?
Well, I wanted to say a couple things about Ada, but maybe you want to wait on that. Or should I go ahead?
So yes, I want to comment something.
I'm also saving this for.
Okay, so I just want to briefly comment something that Dirk has said about about the fact that you are, as much as you can, you want to reuse components. That this is something that is that it is very, very important for the automotive industry. And I think this is in fact a very interesting challenge, because you are developing new components that rely on acceleration features, GPUs, FPGAs, EPUs, etc., and you want to connect them with the components that already exist. And this is, in fact, a host acceleration model that is implemented by many different programming models, including OpenMP. And I have to say that as OpenMP is evolving, the heterogeneous model, the accelerator model is improving. So here I think there is still a great opportunity to, despite automotive industry is more interested on this, let's say, coarse grain level, parallel execution, because of these very dedicated accelerated components, the accelerator model is going to play a key role here. And here I think OpenMP can say a lot of things, because the acceleration model of OpenMP allows to easily describe how the host and the device interact. And so between existing components and those news that are exploiting these GPUs, for example, features, we can still communicate in an easy way using programming model. And here, of course, I'm not only or OpenMP, but the same applies to Ada.
So you want to take it?
I was going to say a couple of things. One, it's interesting that Dirk mentioned simulation. AdaCore has recently released a product that is a qualifiable code generator from Simulink to the subset of Ada called Spark, which is intended for formal verification. And the currently it's really just used to create code that runs. And the transformer, the code generator, is in the process of being certified so that you can skip a lot of verification steps, because you can treat essentially do your testing at the model level, and then you have confidence that the same thing will hold. But over time, the way direction we're going is allowing you to specify some properties at the model level and have those properties turned into contracts at the Spark level. And so I just wanted to quickly introduce the additional contracts that we think are important for parallelism. And I'm going to share my screen again, if you don't mind. So I don't know if you're familiar with the Spark language, but one of the fundamental concerns when you're talking about any kind of parallelism, whether it's sort of fine-grained or coarse-grained, is what are the side effects of computations that are not visible at the interface to the module doing the computation. And in Spark, those are something you have to actually declare, or you can have the tool sort of infer it from your code. But in any case, these kinds of global contracts are critical to doing any sort of static analysis of the safety of a multi-core, multi-parallel system. And they identify what sorts of side effects, what sorts of global variables you're manipulating, and whether those global variables are self-synchronized in the sense they're locked, they're somehow atomic, or they somehow lock themselves, or they aren't, in which case you really have to be sure that you don't have two operations occurring simultaneously that be manipulating the same data object. So one of the things that we're borrowing from Spark for Ada22X because of the growing importance of parallelism is this notion of a global contract. We already stole preconditions, postconditions, various kinds of invariants, which are great for sequential code and for abstractions, but it doesn't tell you much about safety with respect to parallelism. So this is one of the things that we think is kind of critical to languages that are going to be using providing parallelism. The other one has to do with deadlocking and general notions of, well, where are you going to be blocking indefinitely? And systems that do a lot of complex multi-core, you can end up with a sort of a deadlock without knowing it. And so part of the additional contract that we're adding to Ada22X has to do with where are you allowed to block and where are you not allowed to block, and you're promising you're not blocking, and the compiler enforces these contracts. That's sort of part of the deal. Yeah, here's what I promise, and someone had better check that those promises are true. And the last thing that I wanted to mention is that once you have this additional data, then the compiler has the ability to do conflict checking, which basically means, do you have two simultaneous activities, updating or reading plus one updating the same data? And that problem is not fully solved for general programming languages, partly because of the use of pointers and various other things. For Spark, it is a solved problem, and that's kind of a cool thing about Spark, is it does have full conflict checking, but it's not a solved problem for a more general purpose language. So we've defined various levels of checking. You can say, oh, I don't want to need any checking. Programmer is in charge. A middle level where you're sort of looking for checks that are, clearly wrong things are going on, and then a more conservative check. And I noticed that OpenMP has dependency annotations. For Ada, we really want those to be generated by the compiler. Yeah, I suppose the programmer could write them, but then what happens if they're lying? I mean, not that they try to lie, but they sort of assume the best. Or yeah, I think this is the only dependency. Well, actually, no, there's other dependencies, and the compiler is in a position to find those. So in any case, that's where I think the tools should be going, whether it's Ada or other languages that are other tools that want to be used with parallelism in a safety critical environment.
I think you're touching a very interesting point there, which is also an ongoing debate in automotive and certainly at Bosch. So it's where to put those things, right? I mean, traditionally, automotive has been doing C and now C++. And many of the information about contracts and dependency annotations have been come in some sort of like metadata formats. Yeah, I mean, AutoSAR software component template is nothing else than a metadata format describing things like this, and then you always have a separated tool, so not the compiler, but separated tools checking those things. And there's always the problem, as you mentioned, the consistency between the code and what is actually in the metadata. So this is definitely something where let's say, I think the last word is not spoken, although currently also with something like AutoSAR Adaptive, it's going again in the metadata format.
Yeah, I mean, one thing we found exciting is that we do have now a couple of high integrity applications using the Spark subset in the automotive industry. One is in the area of steering wheels, which you think steering wheels, what's the problem with the steering wheel? But these days, a lot of it is steering by wire, and clearly that's it becomes a pretty fundamental issue if someone can interfere with, or if you can have some kind of safety issue with steering. And the other is NVIDIA has a a module that includes GPUs and CPUs, and it has a real-time operating system, a separation kernel that allows you to run applications at different levels of criticality. And that separation kernel is being written using the Spark language. So I think there is interest in pulling formal methods into the automotive industry. It's been there in the aerospace industry for a long time, but now it's beginning to infiltrate, if you will, the automotive industry. And it'll be interesting to see if the parallelism is also part of that formal methods, which I think it should be.
Okay. So in the and also hear Michael's opinion on this, because at the lower level, the architectures are exploited by means of parallel runtimes, and the requirements have been defined with the model somehow, but the people developing parallel programming models might not be that focused on the fulfillment of non-functional requirements, or at least not the majority that are needed in the real-time systems, but on performance. So these programming models need to require these features. So Michael, you mentioned before actually something that I wanted to ask you about, which is the error model, because OpenMP has already been proven as a programmable interface, so it's very suitable for many domains, but there are missing features here. And one of the most important, I believe, is the error model. And you guys have been working a lot on this, but there is nothing yet in the specification. So can you talk about how OpenMP can fulfill these non-functional requirements that are needed in high integrity systems?
I mean, the error model is probably one of the most critical steps, because basically, as you said, there's no the whole API as well as the language semantics were never intended to be used in an environment where functional correctness or well, functional correctness from the application code, but not from OpenMP, was one of the primary design goals, right? So the whole attempt of this error model effort was to add this on top of OpenMP without destroying much of its interface, right? Being a language that also targets C and Fortran, there are very tight restrictions on what you can do in terms of how you would handle an error, right? If you were, say, C++ only, my example in the keynote with the -42 as the number of threads would probably just throw an exception, right? And then you at least have an indication that there was a problem, and then the user code could detect that and do something useful around whatever the safety requirements or the resiliency requirements of that call are in the context of the application that the program is writing. Now, given that we have to support those, let's say, ancient base languages like C and Fortran, the error model becomes way more complicated if operating under this design criterion that we don't want to break backwards compatibility, and we can't really change the interfaces that we're using, especially to the runtime routines. So we had this discussion, and the way OpenMP works is that a lot of the work that we get done is triggered by interest and people who care enough so that we actually get proposals that we can vote on and assess from a technical perspective. And so given that I think at that time the only true embedded systems vendor was Texas Instruments, they had a particular interest in that. The HPC community did not, right? And OpenMP is geared towards performance, so we have to have a good reason if a feature is like -5% on performance, we have to have a very specific and very good reason to put it into OpenMP, because let's say the vision to move OpenMP into the embedded space, if it conflicts with the primary HPC domain, the HPC users won't take it lightly. To make Bosch happy, and a DOE lab in the US with their leadership almost exaflop class machines in the future unhappy by losing 5% of node performance on like an exaflop. That's a whole lot of money that they're losing through that. So the reason why I'm explaining this is, so we are not reluctant to add it. It's just that we have to have good use cases, application use cases, where we can see a benefit that putting that in and accepting the risk of losing performance is actually a benefit for OpenMP. Now, the other aspect, like real time, since I'm an HPC person, I only know like, you know, a marginal amount of this concept. But basically, Edu and through you as well, we're showing proposals how you could extend OpenMP with timing requirements, right? So that you could actually express like deadlines or maximum latencies that you can tolerate in execution. So this is something that where OpenMP needs to learn from other spaces. But it seems, at least from my limited experience, it seems doable. One other point I would like to make is, though, the whole problem that Ada, C, C++, Fortran, and all those languages have, especially also C++ with Parallel STL coming up, is a problem of composability, where Dirk said, you know, at the very top, you basically decompose everything in a bunch of components that all have to somehow interact with each other. And so the problem I saw in the past 20 years almost, when people try to bring together fundamentally different execution mechanisms like OpenMP and threading building blocks, or P threads in OpenMP, or, you know, other parallel programming models that are not really aware of each other, health breaks basically lose. And so having a language like OpenMP, even though it's just the implementation layer underneath, right, will greatly simplify the problem of bringing together ADA components with C components, with C++ components, and make them work together, set aside with all, you know, FUSA and real-time issues. That is a fundamental problem that embedded system builders will have to solve going forward, because the compute capabilities they have to address will greatly improve and increase over time. And they're going to have to solve a computationally expensive problem in their embedded systems. I'm done.
I see all your colleagues agreeing somehow with you, saying like this with their heads.
Well, I think the
Do
notion.
you want to add something?
I was going to say the notion of a shared layer that can be across languages is very valuable. And I think that the distinction between the OpenMP implementation and the OpenMP model is worth making, in that I think certainly when you get into safety critical systems, you pretty much rewrite everything anyway. But if you can preserve the model that is being used on the host, let's say, and is being used more widely, and the compilers are basically the same and so on, but the actual runtime has been written and tuned and maybe subsetted to what you need. So I understand your concern about performance, but it might be that it's an optional feature, and it's present in certain implementations and not in others, and or it's sort of trivial, or it's a scaled back version in some, and it's more important in others. But having this shared model can be very valuable. If everyone is talking about things using the same basic concepts, even if the underlying implementation is completely different, brings a lot of value, I would say. And I think it's similar to what things like Corba and so on have done in the past, where there are lots of different implementations, and there are real-time Corbas, and there are this Corba and that Corba, but the shared model is what becomes the high value item. And I think for OpenMP, it's the same thing, that you've got a nice shared model. I mean, I think one of the challenges with OpenMP personally is that you're trying to hold on to this old process-based view and the task-based view simultaneously. And to me, it feels like at some point you might want to go off and have maybe a safety critical subset of the task side only or something, because I think that's where some of the complexity comes in. When you're trying to sort of walk both of these different paths, that adds complexity, and complexity is evil at any level, but particularly in safety critical systems, every line of code is another line to prove that it's safe, and that's a pain in the neck. So anyway, I think it'd be interesting to come up with a subset of the OpenMP model, as opposed to just start over with a brand new model. I think the OpenMP model has got a nice place to start, but it maybe need to be subsetted for the safety critical world. So
the good thing here is that we already laid the foundations with OpenMP 5 to actually do that. So there's the assumes directive that I was talking about today is one addition that we made in 5.1, but in 5.0 we already introduced what we call the requires directive, where you can say this code requires certain properties from OpenMP and the implementation, as well as the underlying system, like HPC example, GPUs. You can require unified shared memory. And so you could extend that concept to say, this code requires functional safety. And then, you can change the way OpenMP works, because then you can create that subset that you mentioned, or even extend it in a way saying these additional constructs are only available in that restricted context of functional safety or real time or whatever. And you could even mix both, or make them so that you can require FUSA or real time or both.
Yeah, that makes a lot of sense.
So I think Akar was talking about using a subset of the OpenMP specification. But somehow you are already doing this. I mean, if what the programmer sees is Ada, for example, and Ada is built on top of OpenMP, you are already restricted the programmer to use only a subset. So this is kind of a first way of not allowing the programmer of not doing certain things. And in fact, here you have a very interesting that is about this contracts. Okay, that Dirk was saying. Okay, this is a very good thing of using this meta information within the language rather than using this externally. But you already said that these contracts can be built on top of OpenMP by using the dependencies mechanisms, because in fact these contracts maps very well to the dependencies. So we have already built this, this communication. So Dirk can build its system using Ada. Ada is built on top of OpenMP. And in fact, OpenMP is already being used as an API that calls OpenCL. So I know examples. Texas Instrument is using this. The Calray is also thinking of doing this. OpenMP for CUDA is doing exactly this. Okay, so these are a thing that the way we should, rather than really going to the OpenMP specification and let's change this and let's change that, I think a very good approach is let's limit the programmer to use OpenMP by creating layers that are hiding the complexity. Then, of course, you can define certain regions in which the programmer can do whatever it wants. For example, at enable level, okay, within this function, you can implement your very specific functional because you really want to exploit it. But apart from this, I think this is a very good approach to start using OpenMP without really needing to modify it.
Right. I think the reason to try to standardize subsets is that if everybody picks a different subset, then you don't have any interoperability. But you could say, well, we've got a safety critical subset, and everybody's going to, who's interested in safety critical is going to focus on that subset. And if it's not quite big enough, they'll all agree we need to add one more thing to it or something. But if I have my safety critical subset and you have your safety critical subset, we can't share our tools, people have to do different training and so on. So that's the only reason I would argue in favor of defining some of these subsets more in a standard way.
I would like to add just a little bit disagreement to this. And one of the specific examples is I would agree to your statement, Edo, that if you have a compiler that pretty much translates something like Parallelism on top of OpenMP, that this compiler or this transformation can restrict the available subset of OpenMP, right? But at the same time, the implementation of OpenMP can make certain assumptions about how things should behave at runtime. So one particular example is OpenMP doesn't say anything about how long a task may sit in a task pool. Could be forever, essentially, right? Pretty much until the first task may sit there until the last task is executed, and then it's up and for execution. So in certain contexts, you want to change this core behavior, right? And you can only change that when you make that core behavior part of the core language, so that implementations are actually forced to offer you like deadline first scheduling or something as part of the mechanisms that you use, right? So you may still have to, like Taka said, you may still have to have a agreed upon subset of the semantics of OpenMP so that you can target that as a language, and you may make certain assumptions on top when you translate ADA code to that OpenMP specific subset.
Agree.
I mean, one thing we dealt with in Ada is that Ada does have priorities, and OpenMP doesn't really have priorities, or well, the different notion of priorities is not it's not like a hard real-time priority, and that's why we ended up putting each team inside an Ada task rather than sort of having them cross Ada tasks where their priority might not be as well defined. But there are, clearly when you do these mappings, you have to sort of say, what's the right way to do it? And I think the other thing was there was some push to say, well, every feature of OpenMP should be visible through Ada. And it's like, ooh, that's going to be hard. But I mean, a lot of them are tuning. And my sense was, well, tuning is different to me than the fundamental algorithm. Maybe that's unfair, but there's no problem having additional pragmas or funny APIs, whatever, that are sort of on the side, sort of saying, I want to, use this cool feature of OpenMP. It didn't change my algorithm. It just meant that it's going to be more efficient, let's say. Obviously, you wouldn't be using those in a safety critical environment unless that whole subsystem was there. But you could still sort of have fundamentally the same Ada mapping, but then have sort of tuning on the side, if you will. So anyway, that was one of our challenges, is we pretty much decided to settle on one fairly small subset of OpenMP functionality for the language. But then imagine implementations could have as many extra APIs that they wanted, that was sort of their business.
Also, you don't want to have tuning parameters. Yeah, I mean, because the tuning parameters, if they are not implementing or changing actually the functionality, you don't want to have them in the same code at the same piece as the functionality, because I mean, the functionality should be specified, should be portable, and the tuning is platform dependent. So you want to separate that. So having that on the side is actually also a desirable thing.
I think that's one reason I like this syntax.
Interrupt you. Sorry, Tucker. I leave you answer now, but I just want to tell you that we have 3 minutes until 8 p.m. I know you guys, the time flies, and maybe we want to leave some time for the audience to make questions. So sorry for interrupting. Finish the statement, and we can open the.
That's good.
Okay. Sorry. So we didn't cover all the topics we had in the list. But if anyone having questions, you can post them in the chat, or you can just open the micro and ask them yourself. We have a great panelists, so you should be taking advantage of that.
Well, I can I can just make a brief note. I have a problem, which is I'm connected to Ada and to real time and to OpenMP and also in Ampere. So it's kind of difficult to say that I'm against anything that was said in this panel. But I think there's here a set of technologies which we all seem to converge in agreeing that would be very, very interesting to make it happen. Okay, so my issue is how can we make it happen? How concretely? So what can I do tomorrow to make this go forward? Okay, so that's my issue.
I have a very simple answer to this question.
Please, Edu.
That it's work hard in the Ampere project. Those that, okay, very quickly, those that doesn't know what's Ampere. Ampere is an European project in which BSc, Bosch, ICEP, among others, partners, and Michael is also involved as an external advisor, and whose objective is trying exactly to do this, is trying on how we can merge or how we can map a system that is described using some model-driven approach, and how we map this with the underlying pile programming model in the sense of portability. So this pile programming model is used across different platforms. And so how we connect this, how we bridge this.
Do you have money to support a standardization of a safety critical subset of OpenMP?
Not that much.
Oh, well.
Well, with the virus, it's getting cheaper. We're having virtual face-to-face meetings nowadays.
Right, those standardization committees are much cheaper now. I mean, I would certainly be interested in pursuing this further, because I think we definitely are pretty committed at this point to using OpenMP as at least one of our ways of achieving lightweight parallelism. But certainly, if there's a subset that we can all agree on, that is the one we're going to have an implementation, or someone will start building implementations that is are safety critical, that would be very interesting, I think, for the ADO community at least.
So I think that one of the ways to go forward is an actual implementation of the subset, which could be going into some roadmap for certification.
Well, I'd be happy to contribute my work.
I mean, I think what Ada is doing, Ada is already doing this. So if with these contracts, they can guarantee that you have a parallel execution built on top of OpenMP that can be certified, that can be used in safety environment, this is already an excellent example that at least they have already identified a first subset in which we can start working on. So I think this is already a very good starting point.
Yeah.
Obviously, Ada is always a very good starting point.
Come on.
You're here.
Certainly happy to provide that as a starting point, and then pick up.
Because I think what Edu just said is extremely important. Is that this work in the Ada world, in defining a safe parallel model and the mechanisms to make it safe, is indeed a very good first step for what is the safe subset of parallelism for certification. Okay, and I think I agree, that's extremely interesting to.
Let's say a safe subset. I wouldn't say it's the only one, obviously, but it's one that we think is big enough to be useful and small enough to be certified. Cool.
Okay, so Edu, start learning Ada. Lara already knows, so it's only you.
I know a bit. You know a bit.
Well, thank you
Very
all.
easy to learn.
We will pick up our discussions tomorrow, 10 a.m. our time, and who knows what time it is in where you are. But thank you all very much for putting this panel together and participating in it, and the audience for being here and asking good questions. And tomorrow we're going to sort of go to the next level up, in part towards distribution, in parts towards some of the higher level issues that we've been talking about today. And things like trying to combine Ada and C++ and Java into one system. I mean, get ready for that, you know. So anyway, see you tomorrow. Thank you all for coming today. And now we can all have our breakfast, lunch, or dinner, depending on what it is we're waiting for.
Or all three.
Or all three. Okay. Thank you all. See you tomorrow.
Okay.
Stay safe, guys. Bye-bye.
Okay, thank you.